Your body would be stretched to infinity. If you were to fall into a black hole, the first thing you'd notice is that everything starts to look distorted. The light from the stars around you would appear to curve, and time would begin to slow down. But that's just the beginning. Even before you cross the event horizon, your body would already be affected by immense forces. These forces aren't just intense, they're lethal. The most shocking effect is called spaghettification. That's when your body begins to stretch vertically and compress laterally. This happens because gravity doesn't act the same on all parts of your body. The part closest to the black hole is pulled with more force than the part farther away. The result is your body turning into a long thread of matter, like a spaghetti noodle. This process happens so fast that you wouldn't even have time to notice. In small black holes, the stretching starts long before reaching the event horizon. In supermassive black holes, the effect can be more gradual at first, but the end is the same. You turn into a stream of atoms or even less than that. Your body's structure wouldn't survive even for a second. It's not just the physical body that suffers, even the atoms themselves can be destroyed. The gravitational force becomes so intense that the bonds between particles break apart. That means you wouldn't turn to dust or ashes, you'd be undone at a subatomic level. No human body is designed to resist something like that. Not even ships or robots could escape this fate. Spaghettification isn't just a theoretical idea. Scientists have already observed objects being stretched this way around black holes. Stars, gas clouds, comets, and other celestial bodies undergo this. Images show structures being elongated as if they were cosmic chewing gum. This process is so violent that it emits signals detectable from Earth. The reason for all this lies in what are called tidal forces. These are the same forces that cause tides on Earth, but taken to the extreme. In a black hole, the difference in gravity between two very close points can be colossal. This creates a stretching that nothing can resist. That's what happens to anything that gets too close. The scariest part is that from the outside, no one would see you being stretched. A distant observer would see you approaching the horizon slower and slower. In the end, you'd appear frozen, stuck forever on the edge of the black hole. That's an effect caused by extreme time dilation. But you would have been destroyed long before that. The idea of being stretched into an atomic thread might sound absurd, but it's based on solid mathematics and physics. It's not science fiction. These are real calculations about how extreme gravity affects material bodies. And these calculations show that there's no escape. It doesn't matter the size, shape, or composition. Everything stretches until it no longer exists. Some black holes spin, and that adds an even more destructive component. In addition to being stretched, you would also be dragged in high-speed rotation. Matter undergoes such chaotic forces that it disintegrates before even reaching the center. This zone is called the ergosphere, where space-time itself is dragged along with the black hole. It's a region where the laws of physics begin to break down. Scientists are still trying to understand exactly what happens inside a black hole, but what happens outside is already devastating enough. Spaghettification is a brutal reminder of gravity's power in its most extreme form. And the worst part, this process is inevitable once you pass a certain point. No equipment, shield, or known technology can prevent it. This transformation happens to everything: people, ships, planets. Nothing escapes the stretching effect. Even if you tried to approach in a controlled way, at a constant speed, the result would be the same. The fate of anything that gets too close is to be crushed and stretched at the same time. And it all happens in absolute silence, without sound or warning. The point of no return. A black hole is known for its defining boundary, the event horizon. This is the invisible limit that surrounds the black hole, and once something crosses it, there's no coming back. Not for a spaceship, not for a star, not even for light itself. It's called the point of no return because from that line inward, escape becomes physically impossible. The pull of gravity becomes stronger than anything else in nature. If you were floating in space near a black hole, you might not notice the exact moment you cross the event horizon. There's no wall, no flash, no sign. But once you've passed that boundary, you are doomed to move inward. No matter how fast you try to move outward, even at the speed of light, you'd still fall further in. That's how extreme the curvature of space becomes. The reason this happens is that inside the event horizon, all paths, including those that would normally lead away, curve inward. In normal space, you can choose where to go, but in this region, every direction points toward the center of the black hole. Even if you had unlimited fuel and the fastest ship imaginable, it wouldn't help. The laws of physics themselves have sealed your fate. Time also behaves differently near the event horizon. To someone watching from far away, you would appear to slow down more and more as you approach the edge. Right before you cross, it would look like you're frozen in time, hovering just outside. But you, falling in, would feel everything happening at normal speed. It's a strange clash between perspectives, one frozen, one falling. This difference happens because gravity affects time itself. The stronger the gravity, the slower time moves. At the event horizon, time is slowed to an extreme from the outside view. But for the object falling in, time seems to flow normally. It's only after it disappears beyond the horizon that it's lost forever to outside observers. You don't see it vanish, it just fades out. Scientists call this boundary event horizon because events inside it can never be seen from the outside. It's not that the light gets blocked, it simply can't escape. Any signal, any message, any data that tries to get out is trapped. It's like throwing a message in a bottle into a waterfall. It never reaches the surface. The event horizon hides everything that happens beyond it. This is why black holes are so mysterious. We can't observe what's inside. We can only detect what happens near the edge. We rely on the behavior of matter swirling around or the flashes of radiation given off just before something disappears. It's like watching shadows dance behind a curtain. You know something is happening, but you can't see what it is. The size of the event horizon depends on the black hole's mass. The more massive the black hole, the wider the horizon. For a black hole as massive as our Sun, the horizon would only be a few kilometers across. But for the supermassive black hole at the center of our galaxy, it stretches millions of kilometers. Yet no matter how the size, the rule is the same: cross it, and you're lost. Even light, the fastest thing in the universe, can't escape once it crosses that boundary. That's why black holes are black. They emit no light from inside the event horizon. It's not a shadow or a dark object. It's a complete absence of escape. The space inside isn't filled with anything you can see. It's an abyss beyond measurement. If a planet or spaceship were to fall into a black hole, we wouldn't see it hit the center. We would only see it freeze and fade as it nears the event horizon. We could measure the gravitational effects, maybe detect a burst of radiation as it gets torn apart, but we'd never know what happens in the final moments. Those details are lost to the outer universe. This limit also causes deep problems in physics. We don't know what happens to information that crosses the event horizon. Does it get destroyed? Does it stay inside? Does it somehow escape in a scrambled form later? This mystery, called the information paradox, has puzzled scientists for decades. It challenges the idea that information can't be lost. One thing is clear: the event horizon is not just a border, it's a one-way trap, enforced by the laws of space and time themselves. Once crossed, no return is possible. That's what makes black holes so terrifying. Not the destruction, but the complete and permanent disappearance of everything that falls in. Time nearly stops near them. Time doesn't work the same way near a black hole. The stronger the gravity, the slower time moves. This isn't just science fiction, it's a real effect called gravitational time dilation. Near a black hole, time can slow down so much that seconds for you become hours, days, or even years for someone far away. The closer you get to the event horizon, the more extreme the effect becomes. If you were floating near the edge of a black hole, you might only experience a few minutes, but someone watching you from a safe distance might see those minutes stretched into years. It's like being in a slow-motion bubble where everything around you is racing forward. Meanwhile, your clock barely ticks. Time stretches and warps in a way our brains struggle to imagine. This effect isn't just a theory. We've seen hints of it in real experiments. GPS satellites, for example, need to adjust their clocks because of gravity's impact on time. The difference near Earth is tiny, but near a black hole, it becomes extreme. Gravity bends space, and that bending affects how time flows. Near a black hole, time almost comes to a stop. If you could survive near a black hole long enough and then fly back to Earth, you would find that everyone you knew had aged far more than you. You would have moved through time at a different rate, a one-way ticket to the future. This idea forms the basis of some time travel concepts, but it's not a trick or a machine. It's the natural effect of extreme gravity. This is one reason why black holes fascinate scientists. They let us test theories of time, space, and gravity in their most intense forms. No other object bends time this much. Near the event horizon, clocks basically stop. But for you, falling in, everything feels normal. That mismatch is one of the most mind-bending aspects of black holes. Time dilation also affects what we see. If a spaceship falls into a black hole, an outside observer would see it slow down endlessly, never quite crossing the horizon. But the people on the ship would feel themselves falling quickly. For them, it's a fast journey. For observers, it's frozen in time. Two versions of the same event, shaped by gravity's pull. The stronger the black hole, the more extreme the time distortion. Around a small black hole, time doesn't slow as much before you're destroyed. Around a supermassive one, the time effects become huge, and the journey may last longer before tidal forces rip you apart. So even the way time behaves depends on the size and mass of the black hole. This distortion of time is not just a curiosity, it affects how we interpret the universe. Light from matter falling into a black hole gets stretched out, becoming redder and fainter. This gravitational redshift shows us how much time is slowing down. It's a visual clue that lets scientists study black holes indirectly by measuring the time-bending effects. If two observers try to measure the same event near a black hole, they will get wildly different results. One might say it happened instantly. The other might say it took centuries. That's not a mistake. It's a built-in feature of how time and space interact. It shows how our universe is flexible and how time is not absolute. This is why many movies and books use black holes in time travel plots. There's truth to the idea that you can experience less time than others just by getting close enough to extreme gravity. But in reality, you wouldn't survive long enough to enjoy it. The forces are too strong, and even if you could, coming back might not be an option. In theory, time at the event horizon stops completely from the perspective of someone far away. It's like pressing pause on a cosmic scale. But for the falling object, everything continues until destruction. Two realities happening at once, depending on where you are. It's a strange and disturbing effect of Einstein's relativity. So when we say time nearly stops near a black hole, it's not exaggeration, it's physics, and it shows just how far black holes push the rules of our universe. They don't just bend matter, they stretch time into strange and dangerous shapes. Jets that tear galaxies apart. Some black holes don't just pull things in, they also fire matter out. These are relativistic jets, massive beams of particles launched from the regions near black holes. They travel at nearly the speed of light, shooting out in opposite directions, and in some cases, they stretch for hundreds of thousands of light years. These jets can rip through entire sections of galaxies. The jets aren't coming from inside the black hole itself. They form in the disk of superheated matter swirling around it. Magnetic fields in that disk twist and snap, accelerating particles outward. The result is a focused, high-energy beam. It doesn't shine like a flashlight, it's more like a cosmic blowtorch. Relativistic jets are among the most powerful phenomena in the universe. They carry radiation, heat, and high-speed particles. These jets can destroy stars, blow away gas clouds, and stop new stars from forming. When aimed into space, they carve tunnels through interstellar material. When aimed at a galaxy, they can shut down its growth. These jets come from supermassive black holes at the centers of galaxies. When these black holes are actively feeding, their disks become extremely energetic. The energy has to go somewhere, and some of it escapes as jets. They don't fire in all directions. They launch in narrow beams, often perpendicular to the disk. We've seen entire galaxies distorted by these jets. In radio telescope images, huge lobes of emission stretch far beyond the galaxy's visible edge. These are signs of matter being pushed out for millions of years. The jets can reach distances far beyond the host galaxy itself. They leave scars in space, marking the path of destruction. Some galaxies, like M87, have visible jets extending for thousands of light years. In that case, the jet is so bright in X-rays that it's visible across the universe. And yet, it all comes from matter that didn't fall into the black hole, but was redirected by magnetic forces. The black hole feeds, but also flings. These jets can also regulate galaxy growth. By blowing gas out of the galactic center, they prevent new stars from forming. It sounds destructive, but it may help galaxies stay balanced. Too much gas would cause rapid star formation, leading to instability. The jets act like a control valve, releasing pressure. But the downside is that jets can sterilize whole regions of space. Clouds that could have formed stars and planets are scattered or evaporated. If a young solar system were caught in a jet's path, it would be stripped and fried. There would be no chance for life to form. That's how destructive these beams can be. Jets also show us how black holes affect things far beyond their own borders. A single black hole, just a few dozen kilometers wide, can alter a region of space millions of light years across. That scale of influence is hard to grasp, and it happens without the black hole ever leaving its central position. We still don't fully understand how these jets stay so focused. They don't scatter easily, even over vast distances. Some theories involve spinning black holes and complex magnetic fields. The physics at play near the black hole's edge are still being studied, but we know the results: long-range devastation. Not all black holes produce jets. Only the ones that are actively feeding and have the right conditions do. But when they form, they can last for millions of years. During that time, they keep clearing space, pushing matter away, and leaving trails of energy. They are cosmic weapons of unimaginable reach. For any civilization unlucky enough to be in the path of a jet, there would be no warning. Just a burst of radiation strong enough to vaporize worlds. That's not a movie plot. That's how the universe works at high energy. And these jets are real, visible, and terrifying. Their growth is nearly unlimited. Black holes can grow far larger than most people realize. While they often start as the collapsed core of a massive star, that's just the beginning. Over time, they feed, and the more they eat, the more powerful they become. There's no upper limit we've confirmed. Some black holes have grown to billions of times the mass of our Sun. This happens through a process called accretion. Matter falls into the black hole, usually gas, dust, and stars. As it gets pulled in, that matter heats up and emits energy. Then it crosses the event horizon and disappears. Each piece of matter adds to the black hole's mass. The process is simple, but relentless. Supermassive black holes probably started small long ago, but over billions of years, they consumed everything around them: stars, planets, clouds, even other black holes. The more they consumed, the more they grew. Eventually, they became giants, dominating the centers of galaxies. Every large galaxy we've seen has one. In some cases, black holes merge with others. When two galaxies collide, their central black holes often spiral together and become one. This adds huge amounts of mass all at once. The resulting black hole is bigger, more powerful, and often more active. These mergers help explain how some grew so quickly. Some of the biggest black holes are in quiet galaxies. Even though they aren't feeding right now, their size shows they must have consumed incredible amounts in the past. One example is Tone 618, a black hole with over 60 billion solar masses. That's bigger than many galaxies. And yet, it formed through ordinary feeding and merging. There's no known upper boundary for black hole size. The only limit is the amount of matter nearby. If a black hole is placed in a dense environment, it will continue to grow. The process only slows down when it runs out of fuel. But in rich clusters of galaxies, there's plenty to eat, so the growth can continue indefinitely. Black holes don't just passively wait for food. Their gravity pulls in nearby objects. If they're in the center of a galaxy, they naturally attract gas and stars. Some scientists think early black holes formed in dense regions and immediately started feasting. This would explain why some supermassive ones appeared so early in cosmic history. Their influence grows with their size. A more massive black hole has a larger event horizon, a stronger gravitational pull, and a greater effect on its surroundings. It bends space more. It slows time more. It clears out more material from the galaxy center. The galaxy becomes shaped by the black hole's presence. Some black holes are so massive, they don't even fit well in simulations. They break models, raise questions, and force scientists to revise theories. How could they have formed so fast? How did they grow this large without disrupting their galaxies? These mysteries show we still don't understand black hole growth completely. What we do know is that black holes don't shrink naturally. They only grow. Hawking radiation, a kind of slow evaporation, exists, but is too weak to matter for large black holes. So, over cosmic time, they accumulate more and more mass, and as long as they have fuel, they keep going. Eventually, in the far future, black holes may be the last massive objects left in the universe. Long after stars die and galaxies fade, black holes will remain. Not because they're immortal, but because nothing else matches their ability to grow and endure. Their hunger has no natural ceiling. When we say their growth is nearly unlimited, we mean it literally. The universe may not have created an upper limit for how big a black hole can get. We might only be seeing the beginning. If one passed through Earth, it pierces twice. Primordial black holes are tiny black holes that may have formed just after the Big Bang. Some of them could be as small as a mountain, but incredibly dense. If one of these passed through Earth, it wouldn't crash, it would pierce. It would go straight through like a bullet, leaving a trail of destruction in its wake. But we wouldn't see it coming. The gravity of such a black hole would be focused and intense. As it enters the planet, it would compress the matter around it, possibly creating a seismic shock. As it moves through the core and exits the other side, it might cause another shock wave. This wouldn't be an explosion, but a tunnel of disruption. Our planet could survive, but not without scars. The path of the black hole would likely destroy anything in its immediate line. It could vaporize rock, distort magnetic fields, and possibly trigger earthquakes. Most of the Earth would remain intact, but the affected regions could experience catastrophic events. Worst of all, we wouldn't know until it happened. There'd be no warning. Because these black holes are so small and dark, detecting one ahead of time is nearly impossible. They don't emit light unless they consume something, and even then, the signal is faint. If a primordial black hole passed near Earth, we'd likely only detect its gravitational pull or its aftereffects, and by then, the damage would already be done. The actual hole it would leave behind wouldn't look like a tunnel. Earth's own gravity and heat would close it up quickly. But deep within the planet, material could be permanently rearranged. Some models suggest a line of melted rock and disturbed layers would remain. It would be a geological scar, invisible on the surface but massive below. A black hole like this would likely pass straight through and keep going. Earth's mass isn't enough to slow it down significantly. It would enter, pass through the core, and exit on the other side, all in minutes. Then it would continue drifting through space, having wounded the planet, but not staying. That's the danger of such compact, fast-moving objects. Some scientists have looked for signs that this may have happened in Earth's past. Unexplained seismic patterns or strange alignments in the crust could hint at a cosmic visitor, but so far there's no confirmed evidence. That doesn't mean they aren't out there, only that they're very good at staying hidden. If one of these black holes were to pass near a city, the results could be devastating. The gravitational effect alone could damage buildings or infrastructure, but it would depend entirely on the path it took. A direct hit would be catastrophic. An indirect pass might only cause slight shifts or vibrations. Unlike an asteroid, a primordial black hole wouldn't burn in the atmosphere. It wouldn't make a crater. It would go in clean, almost silent, and leave destruction beneath the surface. From a distance, it might not even look like anything happened until sensors and instruments picked up strange activity. There's ongoing research into the possibility that dark matter might include primordial black holes. If true, the universe could be filled with them. Most would never come close to us, but it only takes one. Earth is moving through space, and so are they. Crossed paths are unlikely, but not impossible. What's most unsettling is that we have no known way to stop one. They're too small to detect early and too fast to intercept. We couldn't destroy it, and trying to block it would fail. The only real defense is distance and luck. So far, we've been lucky. And if one ever does hit us, We might not realize it until it's already gone, and the planet is forever changed. There's a monster at the center of our galaxy. At the center of the Milky Way, about 26,000 light-years from Earth, lies a supermassive black hole. It's called Sagittarius A*, and it weighs over 4 million times the mass of the Sun. It doesn't move, it doesn't glow brightly, but its influence is enormous. It controls the movement of stars and shapes the very core of our galaxy. And sometimes it wakes up. Sagittarius A* is usually quiet, but occasionally it flares. These outbursts come from matter getting too close and being swallowed. The flare emits X-rays and infrared light that travel across space. These flashes don't last long, usually just hours, but they tell us the black hole is still active, even if it sleeps most of the time. Around Sagittarius A*, stars orbit at incredible speeds. Some move so fast it takes just a few years to complete a full loop. This motion tells us that something extremely massive and compact must be there. And since no light comes from the center, a black hole is the only explanation. We can't see it directly, but we can see its impact. In 2022, astronomers released the first direct image of its shadow. Using a global network of radio telescopes, they captured the bright ring of matter around the black hole. It matched predictions, a glowing ring surrounding a dark void. That shadow is the closest we've come to seeing the monster itself. Sagittarius A* doesn't currently consume much matter, but that might change. If a gas cloud or star gets too close, the black hole could enter a feeding phase. During such periods, the galactic center would become much brighter and more energetic. Past events suggest this may have already happened thousands of years ago. Scientists found signs of ancient outbursts from Sagittarius A*. Massive bubbles of radiation stretch above and below the Milky Way's plane. These Fermi bubbles may be the result of powerful jets or winds from the black hole in the past. They're like cosmic fossils, leftovers from an active and destructive phase. The influence of Sagittarius A* extends far beyond the galactic core. Its mass helps keep the inner stars in orbit and affects the structure of the galaxy. Even though it's just one object, its gravity shapes billions of others. Without it, the Milky Way would likely look very different, and maybe wouldn't exist at all. Other galaxies also have central black holes, some far bigger, but ours is the closest example we can study in detail. It provides a natural laboratory for understanding black hole behavior, and every new observation helps refine what we know about gravity, space, and time. There's even a star called S2 that orbits Sagittarius A* in just 16 years. By tracking its movement, scientists have tested Einstein's general relativity in extreme conditions. So far, the results match the theory, but more data is coming. This black hole helps confirm physics at the edge of what we can observe. Even though it's huge, Sagittarius A* is still mysterious. We don't fully understand how it formed, or why it remains relatively quiet. Some think it had violent beginnings. Others believe it's waiting for its next meal. Either way, its silence is not safety, just a pause. One thing is clear, it's not going anywhere. Sagittarius A* will outlive the Sun, Earth, and probably the Milky Way itself. As stars die and galaxies collide, it will remain at the center, consuming, controlling, and waiting. And it's closer than you might think, just 0.003% of the galaxy away from us. They outshine galaxies before devouring matter. Before a black hole swallows matter, it often puts on a dazzling show. As gas, dust, and stars spiral inward, they heat up. The friction and compression in the accretion disk make the material glow, brighter than anything else in the universe. In fact, some black holes shine more than entire galaxies, but the light comes from the struggle before the end. This glowing material doesn't come from inside the black hole, it's from the edge, just outside the event horizon. As matter falls in, it speeds up and gets squeezed. That energy turns into radiation, X-rays, ultraviolet, and visible light. What we see is the last burst of energy before total silence. Quasars are extreme examples of this. They're supermassive black holes in feeding mode, surrounded by blazing disks. Some quasars are visible from billions of light-years away. They emit more energy than thousands of galaxies combined, and yet the source is just one black hole consuming nearby material. This light can be so bright that it hides the galaxy behind it. When we first discovered quasars, we didn't even know they were attached to galaxies. Only later did we realize they were powered by hungry black holes. Their brightness isn't a star, it's destruction on a massive scale. Accretion disks are extremely hot, millions of degrees. That heat creates jets, winds, and turbulence. The matter glows fiercely as it loses its last bit of freedom. Then it vanishes beyond the event horizon. The light stops. What was once a brilliant source of energy goes completely dark. The glowing phase doesn't last forever. Once the black hole runs out of nearby fuel, the disk fades, the light dims, and the black hole returns to silence. But the memory of its hunger remains. We see the scars in surrounding space, shocked gas, disrupted stars, empty zones. Scientists use this light to study black holes indirectly. By analyzing the radiation, we can estimate the mass and spin of the black hole. We can map the temperature and flow of matter in the disk. We even use timing patterns to understand how matter spirals inward. It's one of our best tools for exploring what we can't see directly. Some black holes enter and exit this bright phase over time. If a passing star comes too close, it gets torn apart and creates a temporary flare. This flare may last days, weeks, or months. Then it fades. It's a brief flash, like a cosmic heartbeat, telling us the black hole is still active. The light we see from these events is ancient. If a black hole flared a billion years ago, we're only seeing it now. We're witnessing history, events that ended before Earth even formed. But that also means we can study black holes across time. We're watching how they behave across the life of the universe. The most powerful light in the cosmos often comes from the edge of darkness. That paradox, brightness before oblivion, is what makes black holes so fascinating. They don't just destroy, they shine, flare, and signal their presence before doing it. And then they vanish again. They outshine galaxies for a moment. They light up the universe with warning flares. But then they take everything, including the light, and disappear. Some may explode in a burst of radiation. Not all black holes last forever. According to a theory by Stephen Hawking, the smallest ones slowly evaporate. This process is called Hawking radiation, and it happens because of quantum effects near the event horizon. Over time, energy escapes and the black hole loses mass. For small black holes, this could lead to a final burst, an explosion of deadly radiation. The smaller the black hole, the faster it evaporates. Large black holes, like the ones in galaxies, lose mass so slowly it's unnoticeable. But a small one, like a hypothetical primordial black hole, could evaporate entirely within the current age of the universe. In its final moments, it would release a huge amount of energy. This might appear as a powerful gamma-ray burst. Gamma-ray bursts are among the most energetic events in the universe. Most are thought to come from collapsing stars or neutron-star mergers, but some might come from evaporating black holes. If a tiny black hole reaches the end of its life, its last moment could release a sharp, short-lived flash of intense radiation. Scientists are still searching for this signal. We haven't confirmed Hawking radiation yet. It's a theoretical prediction based on combining quantum mechanics with gravity. If it's real, it means black holes are not truly eternal. They can lose energy and shrink. And when they get small enough, the final seconds could be violent, a mini-bang in space. A black hole explosion wouldn't be like a fireball or mushroom cloud. It would be a release of particles and radiation, invisible to the eye. But gamma rays can travel across space and damage anything in their path. If one happened close to Earth, the radiation could strip our atmosphere or harm electronics. Thankfully, such events are expected to be rare and distant. Primordial black holes, if they exist, might be evaporating right now. These are thought to be relics from the early universe, formed from dense pockets of energy just after the Big Bang. Some could still be around, and some might be reaching their end. Detecting one would confirm not only their existence, but Hawking's theory too. If we could observe an evaporating black hole, it would change physics forever. It would link quantum mechanics, general relativity, and thermodynamics in one real-world event. The data from a single burst could unlock mysteries about the structure of space-time. That's why astronomers keep their eyes open for unexpected gamma-ray flashes. There are missions scanning the sky for such bursts. Space telescopes like Fermi and Swift look for unexplained flashes. So far, no confirmed black hole evaporation has been found, but scientists continue to monitor the sky, hoping for that one unmistakable signal. It could be quick, a fraction of a second, but meaningful. Evaporation also means black holes might not be permanent fixtures in the far future. Over trillions of years, even the biggest ones could shrink. They would fade, flicker, and eventually vanish with a final release of energy. The universe would lose its last massive objects in flashes of radiation. It's a long way off, but still part of the picture. The idea that black holes can die is strange. We usually think of them as the end, the destroyers. But in this model, they have a lifespan. They are born, they feed, and eventually they evaporate. Their final act is not silence, but a burst of energy. Even their death is violent. Hawking radiation is one of the few ideas that blends quantum physics with gravity. It's still theoretical, but widely accepted as possible. If we ever detect it, it will prove that black holes are more than just cosmic drains. They interact with the universe in deeper, more complex ways than we imagined. So some black holes may not just sit in darkness forever. They may end their lives in a final scream of energy, a short, sharp flash that says goodbye. Star cemeteries exist in space. There are regions of space where stars used to shine, but no longer do. These zones have been wiped clean by the influence of black holes. They've pulled in stars, gas, and dust, leaving behind dark, empty shells. These areas are sometimes called stellar graveyards. In them, only remnants remain, or nothing at all. At the centers of some galaxies, the black hole is so active that it pushes away material. The jets and winds can heat up and blow out gas that would have formed new stars. Without that gas, no new stars are born. Over time, the existing stars die, and the region becomes dark and lifeless. It's not a quiet death, it's a forced extinction. Some black holes go further than just preventing new stars. They actively consume the old ones. Stars that wandered too close get stretched, shredded, and devoured. Over millions of years, this process clears entire zones. The stars that once orbited peacefully are either eaten or flung away. What's left is a void where a thriving region used to be. In galaxy clusters, we sometimes find fossil galaxies. These are galaxies that appear unusually dark. They have fewer stars than expected, and the core is strangely empty. Scientists believe their central black hole grew too large and too active. It destroyed the very galaxy that gave it birth. What remains is a shell, the tomb of stars. There's also evidence of ancient destruction in the form of gas gaps. These are large regions with almost no hydrogen, the fuel for stars. Observations suggest black holes may have blasted these areas clean. The force of their outbursts pushed gas away, preventing new stars from forming. Over time, these zones became deserts in space. Some black holes don't just affect their own galaxy. Their jets reach beyond, tearing into nearby galaxies and disturbing their structure. In rare cases, an active black hole in one galaxy may destroy the conditions for star formation in another. It's a kind of long-distance kill, proof of just how far their power reaches. These starless zones are hard to study because they emit little to no light. Astronomers rely on X-ray maps, radio waves, and gravitational data to analyze them. What they find is striking. Massive areas of low activity surrounded by richer zones. The contrast shows that something removed the energy and mass, and often that something is a black hole. Even the stars that escape don't always make it. A black hole can slingshot stars at extreme speeds. These stars are ejected from their galaxies and sent drifting through intergalactic space. Alone and cold, they become rogue stars. They shine for a while, then die far from where they were born. It's a slow death sentence delivered by gravity. Over time, these cemeteries grow. The black hole stays at the center, and anything that gets close enough disappears. What once was bright becomes blank. The memory of stars fades, and the region turns dark. For outside observers, the area looks empty, but it wasn't always that way. This process is part of galaxy evolution. Not every galaxy remains rich with stars. Some age into silence because of their central black hole's hunger. Others are interrupted by mergers or chaos. But when black holes clear out an area, the result is final. No light, no birth, no renewal, just absence. Astronomers use the term quenching to describe this shutdown. It's when a galaxy stops producing stars. And in many quenched galaxies, the central black hole played a role. Its jets, winds, or growth disrupted the delicate balance of star-making. It became the cause of cosmic extinction. So yes, there are real star cemeteries in space, places where black holes have erased what once lived. Not by accident, but by dominance. Do they destroy information forever? One of the biggest puzzles in physics is what happens to information inside a black hole. According to quantum theory, information can never be truly lost, but black holes seem to violate that. When something falls in, a star, a planet, a book, or a person, it disappears. What happens to the data that defined it? Does it vanish too? This is the heart of the information paradox. General relativity tells us that black holes trap everything beyond the event horizon. Nothing escapes, not even light. But quantum physics says information about particles must be preserved, even if they transform. These two ideas clash at the event horizon, creating a problem. Imagine throwing a document into a fire. The paper burns, but the smoke and ash still contain traces of what it once was. In theory, you could reconstruct it. But with black holes, there's no ash. The matter falls in, and the black hole only keeps its mass, spin, and charge. Everything else, the story is gone. That shouldn't be possible. Stephen Hawking initially believed the information was lost forever. He argued that once matter entered a black hole, it was gone, and its information destroyed. But that view caused major issues for physics. If true, it would mean quantum mechanics is incomplete or wrong, so scientists pushed back hard. Later, Hawking revised his stance. He proposed that information might somehow be encoded in the radiation that black holes emit over time. This radiation, called Hawking radiation, carries energy, but maybe also clues. It's extremely subtle and hard to measure, but it offers a possible solution. The information isn't lost, just scrambled. Some theories suggest the information is stored on the surface of the event horizon, not inside, but at the edge. This idea, known as the holographic principle, says that all the data about what falls in is imprinted on the horizon itself, like a cosmic hard drive. It's not destroyed, just transformed. Other proposals involve firewalls, energetic zones that destroy matter at the horizon. But that raises new questions about what counts as destruction. Is it enough for the information to be changed? Or does it need to be recoverable? The debate continues with no clear winner. Quantum gravity, a theory that unifies quantum mechanics and gravity, might one day solve this. But right now, we don't have a complete theory. All we know is that the question of information pushes physics to its limits. It shows where our understanding breaks down and where the next big discovery may lie. Some physicists think that when black holes evaporate, they release information slowly. Others think the information stays locked up forever. And some believe black holes might be portals to other universes, and the information goes there. All of these are speculative, but serious ideas under study. What makes the paradox so important is that it touches the core of science. Information is everything in physics. If it can truly be destroyed, our laws need rewriting. But if black holes preserve it in some strange form, then we just haven't figured out how to read the message yet. This isn't just about stars and gravity. It's about how the universe stores, moves, and respects data. A black hole may be the ultimate test of how nature works, and until we solve the paradox, we won't fully understand space, time, or the limits of reality. A single dust grain makes them stronger. Black holes grow by consuming matter. It doesn't have to be a planet or a star. Even something as small as a dust grain adds to their mass. That's because black holes follow the basic rule of gravity. Anything they absorb stays with them. They don't lose mass, they only gain. Every particle that crosses the event horizon becomes part of them. This means black holes never shrink from eating. There's no limit to what they can take in. Gas, dust, photons, particles, anything with mass or energy. Even something microscopic becomes part of the black hole forever. One tiny grain may not seem like much, but over time it adds up. Billions of years of slow accumulation make a big difference. The process is simple but relentless. A black hole pulls in matter, swallows it, and gets heavier. And the more massive it becomes, the more it can pull in. It's a cycle. Growth leads to more gravity, and more gravity leads to more growth. That's why even the smallest addition helps strengthen the black hole's power. This constant gain in mass makes black holes extremely stable. Unlike stars, which can burn out or explode, black holes don't decay, at least not naturally. They just sit and wait for matter to come near. Even a passing atom gives them more mass, even if by a tiny amount. They are accumulators in the purest sense. That's part of why they're considered permanent. Unless something takes their mass away, which physics says can only happen slowly through Hawking radiation, they remain. And for large black holes, that evaporation process takes longer than the current age of the universe. So every little gain, even a dust particle, sticks with them for good. Over time, this adds up to something huge. A black hole in a dense environment can grow from tiny to massive just by feeding on small bits of matter. Even if it never swallows a star, it could still become dangerous. Constantly eating dust, gas, and debris from its surroundings, it grows silently. That's why some are bigger than we expected. This helps explain how black holes formed so quickly in the early universe. Even in the first billion years, some grew to supermassive size. They didn't need to eat stars constantly, just enough material over time. Every grain, every particle of hydrogen added to their mass, quietly making them giants. This also means black holes don't waste anything. When they absorb matter, it all goes in. There's no digestion, no release, no leftovers. Whatever crosses the horizon becomes part of the black hole. Even light itself, if trapped, adds to the black hole's energy. That's how complete their capture is. This behavior is what makes black holes unique among cosmic objects. Most things lose mass, radiate energy, or change form, but black holes only gain. They don't break down matter, they trap it. And once it's inside, it never comes back out. Even if the black hole does nothing for millions of years, it still keeps growing by collecting tiny pieces. It's why black holes are sometimes compared to cosmic garbage compactors. But that's not quite accurate. They don't crush matter into space-saving form, they keep it as mass, making themselves heavier. That extra mass increases their gravitational pull, which pulls in more matter, which increases their pull again. So even if nothing large falls in, black holes keep growing, one dust grain at a time. It's a slow, quiet kind of power, the kind that lasts forever. No explosions, no sounds, just a steady increase. And it makes them more permanent with every passing second. That's why no addition is too small. A black hole doesn't care if it eats a star or a speck. To it, all mass is fuel, and that makes it unstoppable. If Earth orbited one, it would freeze. Imagine if Earth orbited a black hole instead of the Sun. Even if the orbit were stable, the consequences would be deadly. The Sun gives us light and heat. Without it, our planet would be plunged into eternal night. A black hole doesn't shine unless it's feeding. So if Earth circled a quiet black hole, the sky would be black, and temperatures would drop fast. Within weeks, the surface temperature would fall below freezing. Oceans would start to solidify. Within a year, most of the planet would be covered in ice. Life as we know it depends on the sun's warmth and light. Without it, plants couldn't photosynthesize, and the food chain would collapse. Some heat would remain for a while. Earth's core would still emit geothermal energy. Radioactive decay would keep underground areas warm for a time, but surface life would vanish. Only deep-sea vents and underground bacteria might survive. The Earth would become a frozen rock in space. Even if the black hole were massive, it wouldn't help. Unless it had a glowing accretion disk, it would provide no light, and that disk would need a constant supply of matter to keep shining. Without it, the black hole is invisible. So the Earth would orbit an object that gives off no visible clues, just cold and silence. This situation could happen in theory. If a star got too close to a black hole and was destroyed, its planets might remain. Those planets could keep orbiting the black hole, but without a star's heat, they'd be doomed, cold, dark, and alone, circling something that offers no warmth or life. Some science fiction stories suggest that advanced civilizations could live near black holes, harvesting energy. In reality, this would require extreme technology and perfect conditions. A planet like Earth, without artificial help, couldn't survive. Our world needs sunlight, both for heat and for biology. Even the day-night cycle would vanish. There would be no sunrise or sunset, no seasons, no shadows, just darkness. The black hole wouldn't provide visual cues, and stars in the sky would appear distorted or bent by its gravity. Light from distant galaxies would curve strangely, making the sky look alien. Earth would also be in danger from other effects. Radiation from nearby black hole activity could be lethal. If the black hole had any jets or flares, they could reach Earth and strip away the atmosphere. Even without that, gravitational tides might disturb tectonic activity. The planet could become unstable. There's also the psychological effect. Darkness affects the brain. Humans are not built for total permanent night. Societies would struggle to maintain order. Mental health would collapse. The beauty of the day sky, blue skies, clouds, sunlight, would be gone. Only cold black space would remain. If Earth were somehow placed in orbit around a feeding black hole, it might get some light. But that light would come with intense radiation. The planet could be cooked rather than frozen. So whether the black hole is active or quiet, the result is extreme. There's no middle ground, only extremes. In some rare cases, rogue planets might already orbit black holes in space. We haven't detected them yet, but it's possible. If they exist, they're likely frozen solid. We'd only detect them if the black hole is active, glowing enough to make nearby objects visible, but most remain in total darkness. So if Earth orbited a black hole, we wouldn't be pulled apart right away, but we'd lose the very thing that keeps us alive, our sun. And that's enough to end the world. Gravitational waves are passing through you now. Right now, as you read this, gravitational waves are passing through your body. They're ripples in the fabric of space-time, created by massive cosmic events. Things like black hole collisions or neutron-star mergers send these waves across the universe. They travel at the speed of light and pass through everything, including you, without resistance. You can't feel them. They don't shake your chair or move your hands. That's because they're incredibly subtle. Even the strongest wave we've ever measured changed space by less than the width of a proton. But that tiny change is real. It stretches and squeezes space itself as it passes. These waves were predicted by Einstein over a century ago, but we only confirmed them in 2015. That's when detectors like LIGO finally picked up the first signal. Two black holes had merged more than 1 billion light-years away. The wave arrived on Earth, and the instruments wobbled, just enough to measure. Gravitational waves don't travel like sound or light. They don't need a medium. They are distortions of space itself, moving through the vacuum of the universe. They compress and expand everything in their path. But because the effect is so small, we only detect the biggest events. They pass through walls, planets, stars, even you, without stopping. No shielding blocks them. They don't reflect or scatter. That makes them hard to detect, but also incredibly useful. They bring us information from places we could never see with telescopes. It's like listening to space instead of looking at it. Every time a black hole collides with another, it creates a wave. That wave travels outward in all directions. Some eventually reach Earth long after the collision is over. Each wave tells a story: the mass of the objects, how fast they spun, and how they moved. We can decode the wave and understand the event. This means gravitational waves are like messages from invisible events. No light, no sound, just movement of space. They tell us what happened in places too dark or distant to see. That's why gravitational wave astronomy is so important. It gives us a new sense, a new way to explore the universe. The detectors that find these waves are huge. LIGO and Virgo use laser beams in long tunnels to measure changes in distance. When a wave passes, the beams shift slightly. It's like measuring the vibration of space using light. These instruments are so sensitive, they must isolate even the smallest noise. So far, dozens of wave events have been detected. Most involve black hole mergers. Others involve neutron stars. Each new detection adds to our understanding. We now know that such collisions happen more often than we thought, and the universe is constantly sending us more waves. Future detectors will be even more powerful. Space-based instruments like LISA will pick up weaker, longer waves. They'll let us hear the early universe, the time before galaxies formed. We'll learn how black holes formed, how galaxies grew, and maybe even detect signals from exotic phenomena we've never imagined. And through it all, the waves will keep passing through you, unseen, unfelt, but real silent tremors from space that ripple through your body, your house, and your planet. Every second, every day. The universe is always moving. You just can't feel it yet. They drag space itself. A spinning black hole doesn't just pull matter in, it twists space itself. This effect is called frame dragging, and it happens when a massive, rotating object pulls the fabric of space-time around with it. Near a fast-spinning black hole, this effect becomes extreme. Space-time doesn't sit still, it swirls like water going down a drain. Anything nearby gets caught in the motion. Even light can't escape the twist if it gets too close. Around these black holes is a region called the ergosphere, where everything is forced to move with the spin. In this zone, space-time itself is being dragged along. You can't remain still even if you try. If you want to escape, you have to move faster than the twisting itself. This dragging effect changes the way orbits work near the black hole. Objects don't just fall inward, they get pulled sideways as well. It's like trying to walk in a straight line on a spinning carousel. The path bends and you're dragged along whether you like it or not. Navigation becomes impossible without accounting for the spin. The faster the black hole spins, the more dramatic the frame dragging. Some black holes are thought to spin near the maximum allowed by physics. Their ergospheres become massive whirlpools, distorting everything near them. The rotation stretches and warps light, matter, and time. It's like entering a spinning funnel of gravity. This spinning creates opportunities too. In theory, it's possible to extract energy from a spinning black hole. The Penrose process suggests that if you drop something into the ergosphere at the right angle, you can split it and send one piece away with more energy than it started with. That energy comes from the black hole's spin. It sounds like science fiction, but it's rooted in solid physics. The idea has inspired speculation about advanced civilizations using black holes as power sources. They wouldn't go near the event horizon, they'd just dip into the ergosphere. It would be dangerous, but possible if technology were advanced enough. Spinning black holes may also play a role in launching relativistic jets. Their rotation helps twist magnetic fields and push matter outward. The faster the spin, the more intense the jets. So even though black holes are known for pulling things in, their spin can also help push things away with devastating force. This dragging effect also affects time. Near a spinning black hole, time slows down, but not evenly. The twist distorts how time flows in different directions. Orbiting with the spin feels different than orbiting against it. It's like being on a moving walkway that changes speed and direction. Everything becomes distorted. Astronomers can estimate how fast a black hole is spinning by looking at the matter around it. The way light is bent, The shape of the accretion disk and the strength of the jets all give clues. We can't see the spin directly, but we can measure its effects. It's like watching leaves swirl in a tornado to guess its speed. Frame dragging isn't unique to black holes. Earth does it too, just very slightly. Satellites have detected the tiny twist in space caused by our planet's rotation. But near a black hole, the same effect becomes overwhelming. It shows how powerful these objects are, twisting the fabric of reality itself. If a spaceship got too close to a fast-spinning black hole, it could be trapped in a spiraling orbit. It wouldn't just fall, it would be dragged sideways and inward at once. Escape would require enormous energy and perfect precision. Without both, it would spiral in forever, twisted by the spinning space-time. So yes, black holes don't just bend space, they drag it. They pull time, light, and motion into a vortex of rotation. And once you're caught, getting out is almost impossible. Their collisions are slow cosmic countdowns. Black hole collisions are some of the most powerful events in the universe, but they take forever to happen. When two black holes get close enough to orbit each other, they begin a slow gravitational dance. They spiral around each other for millions or even billions of years. Every orbit pulls them closer, little by little. It's a silent countdown to a violent end. The energy that draws them together comes from gravitational waves. As they orbit, they lose a tiny bit of energy in the form of ripples in space-time. These ripples travel across the universe, carrying away energy. This causes their orbit to shrink, slowly but steadily. Over vast timescales, they inch toward collision. At first, the loss of energy is small. It might take millions of years to notice a change, but as they get closer, the process speeds up. The orbit shrinks faster, the gravitational waves get stronger, and time accelerates toward impact. It's like water spiraling into a drain, slow at first, then faster and faster. When the final seconds arrive, things happen quickly. The black holes orbit each other at nearly the speed of light. They circle dozens of times in a second. Then they smash together, forming a larger black hole. In that moment, they release more energy than all the stars in the universe, in gravitational waves alone. The collision doesn't create light unless gas or dust is involved. Most of the time, it's completely dark. But gravitational wave detectors can hear the signal. It's a quick chirp, lasting less than a second. That chirp carries all the details: how big the black holes were, how fast they spun, and how they merged. The first confirmed black hole collision was in 2015. Two black holes merged over 1 billion light-years away. The signal took that long to reach us. When it did, our detectors recorded the faintest shift in space, and it changed astronomy forever. We could now observe the universe in a whole new way. Since then, dozens of black hole mergers have been detected. Some involve small black holes, others are enormous. The signals vary, but the pattern is the same: a slow spiral, followed by a quick crash. Every time, the data helps us understand how black holes form, grow, and behave. These binary black hole systems are scattered across the universe. Many are still spiraling. Some won't merge for billions of years. Others may collide tomorrow, or already did, and their waves are just now reaching Earth. We're listening to ancient collisions in real time. These systems might form from stars born together or from black holes that randomly met. In dense star clusters, black holes can sink to the center and find partners. Once they link up, gravity does the rest. The universe is full of these slow dances, playing out over unimaginable timescales. For now, we can only detect the biggest and closest events. Our instruments are improving, And soon we'll hear more distant and subtle collisions. That will reveal even more about how black holes live and interact. It's like tuning into a cosmic radio and hearing stories from the deep past. Each collision is the end of a long story, a journey that took billions of years, and yet we only hear the final beat, the crash at the end of the countdown. The rest remains silent. But in that final second, the universe shakes. And we listen. The Milky Way will feed its own monster. At the heart of our galaxy is a supermassive black hole called Sagittarius A. It's currently quiet, but not harmless. Over time, it will consume more than just dust and gas. It will feast on entire star clusters, clouds, and even small galaxies. The Milky Way is full of material, and the monster in the middle is always waiting. Around our galaxy are dozens of satellite galaxies. These are smaller systems, each with stars, dark matter, and possibly their own black holes. Gravity is pulling them toward the Milky Way. Eventually, they'll fall in and get torn apart. Their stars will be scattered, and their cores pulled into the center. This process is already happening. The Sagittarius dwarf galaxy, for example, is currently being shredded by the Milky Way. Streams of its stars are already merging with our own. Eventually, what remains of its mass may spiral into Sagittarius A, feeding it and making it stronger. As these galaxies fall in, their orbits decay. Their central regions move inward, closer to the galactic core. Over millions of years, their mass migrates toward the black hole. Once close enough, it gets pulled in, star by star, gas cloud by gas cloud. The black hole gains mass, little by little. Each addition makes Sagittarius A more powerful. Its gravitational pull grows. It affects more stars, bends more light, and reaches farther. It becomes harder to escape. And with each new meal, it becomes a greater threat to anything that gets close. This process isn't violent on human timescales. It's slow, smooth, and quiet, but relentless. The galaxy will continue feeding its central black hole for billions of years. By the time it's done, Sagittarius A could be many times more massive than it is now. It may even become one of the largest black holes in the local universe. Our solar system is far from the center, so we're safe, for now. But over enough time, stars can drift inward, orbits change, systems collapse, and regions fall into chaos. There's no deadline, but the process is constant. The center of the galaxy is slowly absorbing its surroundings. Some scientists think that in the very distant future, the Milky Way may become a dead galaxy. Star formation will slow, fuel will run out, and the core will dominate. The black hole, swollen with mass, will sit at the center of a quiet, aging structure, a husk of stars circling darkness. This growth also affects how the galaxy evolves. When the black hole flares up during feeding, it releases energy that can stop new stars from forming. This feedback shapes star birth across the galaxy. It's not just a consumer, it's a controller, influencing what lives and what doesn't. The Milky Way's future includes a collision with the Andromeda Galaxy. When that happens, both central black holes may spiral together and merge. The result will be an even larger monster, born from two galaxies worth of mass. That collision is coming in about 4 billion years. So yes, the Milky Way will feed its own monster. Not in a single moment, but over eons. The center will grow stronger, larger, and more dominant. and it will do so by consuming what was once part of its own body. A galaxy eating itself, one piece at a time. Killer particles from space. Black holes don't just pull things in, they can also launch things out. Near some black holes, especially the active ones, matter doesn't always fall quietly. Magnetic fields and extreme energy around the black hole can blast particles into space. These particles are called cosmic rays, and they move at speeds close to light. Some are powerful enough to damage electronics or even living tissue. Cosmic rays aren't light beams, they're actual particles. Protons, electrons, atomic nuclei, tiny pieces of matter accelerated to incredible speeds. They move through space and can travel for millions of years. Some of them pass right through our bodies, Earth's atmosphere, and even into deep underground labs. Most are harmless, but the most powerful ones are terrifying. Black holes, especially those with strong magnetic fields and spinning disks, act like particle cannons. Matter falling into them gets crushed and heated, and the energy has to go somewhere. Some of it escapes along the magnetic poles, forming narrow, fast-moving jets. These jets can stretch for hundreds of thousands of light years. Inside them are high-energy particles, cosmic bullets. When these particles hit Earth's atmosphere, they smash into atoms and create showers of secondary particles. Most are stopped by the upper atmosphere, but some reach the surface. Others get trapped in Earth's magnetic field, forming the auroras. But at high altitudes or in space, cosmic rays are dangerous. Astronauts receive regular radiation exposure from them. The most powerful cosmic rays can punch through metal. Some are so fast they carry more energy than a baseball thrown by a pro pitcher, all packed into a single proton. We don't fully understand how they reach such speeds, but black holes, especially the biggest ones, are a leading suspect. They provide the perfect environment for extreme acceleration. Not every black hole emits these jets. Only active ones, often surrounded by feeding disks, produce such energetic outflows. But when they do, the results are massive. The jets carve paths through galaxies and shoot out particles across the universe. We've even detected cosmic rays that likely came from other galaxies entirely. There are observatories built just to detect cosmic rays. Places like the Pierre Auger Observatory in Argentina watch for rare, ultra-high-energy particles. Some of them hit detectors only once every few years, but each one is a clue, a data point that tells us something about the violent side of the cosmos. We don't just worry about cosmic rays for science. They pose real threats to electronics, satellites, and even airline passengers. During solar storms, or when Earth's magnetic field weakens, more particles get through. That's why spacecraft are shielded and why astronauts are monitored for radiation exposure. Black hole-launched particles are one of many sources. One scary thought is that these particles are invisible until they hit something. They don't glow or reflect light. You don't see them coming. They just arrive, fast and silent, sometimes with enough energy to disrupt systems or damage cells. On Earth, we're mostly protected, but in space, the danger is real. Some scientists study how cosmic rays may affect Earth's climate or even cause genetic mutations over long times. It's a field full of open questions. We don't know all the sources, but we know that black holes are among the most powerful contributors. These particles are messengers from violent places. The fact that something so tiny, a single proton, can carry such extreme energy is mind-blowing. And the idea that black holes from millions of light years away can shoot them toward us is even more incredible. It's a quiet, invisible danger traveling through space. So yes, black holes shoot killer particles, Not often, not constantly, but with enough force to remind us how extreme the universe really is. Did they form in particle accelerators? Some theories suggest that under the right conditions, tiny black holes could be created in particle accelerators. These would be microscopic black holes, far smaller than an atom. The idea comes from attempts to unify quantum physics and gravity. In certain models, smashing particles at high energy could briefly create a black hole. It would vanish almost instantly. At least, that's the hope. The Large Hadron Collider, or LHC, is the world's most powerful particle accelerator. It slams protons together at near light speed. The goal is to probe the fundamental laws of nature. Some scientists have proposed that these collisions might produce tiny black holes, if extra dimensions or certain physics theories are correct. So far, it hasn't happened. If one did form, it wouldn't be dangerous. Theoretical predictions say it would evaporate in a tiny fraction of a second. That's due to Hawking radiation, a quantum process that lets black holes lose mass. For something that small, evaporation would be nearly instant. It wouldn't have time to grow, pull things in, or escape the detector. Still, the idea caused concern when first proposed. Some feared a black hole might grow uncontrollably and consume Earth, but detailed studies showed that this isn't possible. Even if one formed, it would be too small, too weak, and too short-lived to do any damage. Nature itself creates more energetic collisions every day with cosmic rays. In fact, the Earth's atmosphere is constantly hit by high-energy particles from space. Some of those collisions are even more energetic than anything the LHC can produce. If miniature black holes could be created that easily, Earth would have seen one long ago and survived. That's why scientists feel confident in the safety of the experiments. These ideas come from speculative physics, not mainstream models. They explore string theory, extra dimensions, and quantum gravity. If tiny black holes ever do appear, it would be a groundbreaking discovery. It would offer direct evidence that space works differently at small scales. It would be a major step toward understanding gravity at the quantum level. So far, no black holes have been created, but experiments continue. The LHC and future colliders will reach higher energies. Scientists watch for unusual particle patterns, energy losses, or decay signatures. Anything unexpected could be a sign, not of danger, but of discovery. If a mini black hole did form and evaporate, it might release a unique burst of particles. The detectors would pick up something never seen before. It wouldn't be a fireball or explosion, just a strange fingerprint in the data. Researchers analyze billions of collisions for this kind of anomaly. The idea of making a black hole in a lab sounds like science fiction, but it's rooted in real equations. It's not about creating monsters, it's about pushing physics to its edge. Creating a black hole would mean we finally understand how gravity and quantum mechanics connect. That's the holy grail of modern physics. Of course, not everyone agrees on the theory. Some models say black holes need much more energy than we can reach. Others say they'd never form in a collider at all. It's an open question, one that drives experimental research forward. Until we find one, we just don't know. If it ever happens, it won't be dangerous. It'll be a microscopic event, invisible, brief, and harmless. But it could answer some of the deepest questions in science. What is space? What is time? How does gravity really work? Some clusters are filled with them. Not all black holes are far apart. In some regions of space, dozens or even hundreds of them live close together. These regions are called dense star clusters, and they're some of the most crowded environments in the galaxy. Stars, black holes, and other objects orbit in chaotic, high-speed patterns, and in the middle, black holes may be silently circling each other. Star clusters form from huge clouds of gas and dust. Over time, the most massive stars explode as supernovae. What's left behind? Neutron stars and black holes. In a dense cluster, these heavy remnants sink toward the center. Gravity pulls them together. Over millions of years, the center fills up with black holes. These aren't supermassive black holes, they're stellar mass ones. Each might be a few times heavier than the Sun, but together they create a complex gravitational dance. Some form pairs and merge, others get slingshotted out of the cluster. The result is a dense, ever-changing black hole population in the core. Astronomers believe these clusters may be factories for black hole collisions. The chaos and density make it easier for black holes to find each other and merge. That's where many of the gravitational wave signals we detect might come from, the hidden hearts of star clusters. These regions are hard to study. They're far away, packed with stars, and often surrounded by dust, but computer models help us understand what's happening inside. Simulations show that over time, black holes dominate the cluster core. The lighter stars stay on the outskirts, while the heavy hitters take over the middle. One famous example is the globular cluster 47 Tucanae. It may contain dozens of black holes hidden in its dense core. We can't see them directly, but we observe the stars around them wobbling. That movement reveals invisible masses, and those masses are likely black holes. Some of these clusters may contain intermediate mass black holes too. These are rare, larger than stellar ones, but smaller than supermassive ones. Finding one would help explain how the biggest black holes in galaxies got started. Dense clusters are one possible birthplace. When two black holes merge in a cluster, the new one often gets a gravitational kick. If it's fast enough, it gets flung out of the cluster entirely. These ejected black holes become rogue, drifting alone through the galaxy. So clusters not only create black holes, they also launch them into space. Over billions of years, a cluster can lose many of its black holes this way. The heaviest ones leave, and the system changes. Some clusters may end up with just one central black hole, slowly growing by absorbing others. These lonely survivors become dominant, reshaping the cluster's structure. Clusters are also a great place to study how gravity works in crowded environments. The interactions are complex, with multiple bodies pulling on each other at once. Even small changes can lead to big results. It's like a cosmic game of billiards, but the balls are massive and invisible. In the future, better telescopes and gravitational wave detectors will help us map these black hole-filled regions. We may find that most star clusters hide far more black holes than we ever expected. Quiet, dark, and packed together, a hidden swarm of cosmic monsters. So next time you see a star cluster in a telescope image, remember, it might be filled with black holes, dancing in the dark, waiting for their next collision. They can erase planets without a trace. A black hole doesn't need to flare or explode to destroy something. Sometimes it just quietly devours. If a planet drifts too close, it can disappear. No flash, no noise, no signal. From far away, it would be like the planet simply vanished. Not even light would escape to tell us what happened. This can happen when a planet enters a black hole's event horizon without first being torn apart. If the approach is clean and there's no accretion disk or gas, there's little friction. The planet just falls in. No swirling, no glow, just a silent plunge into the black hole's core. It's gone instantly. Most black hole feeding events we see involve light and radiation. That's because the matter heats up before falling in. But if there's no resistance, like with a dead, rocky planet, there's no light. It just sinks. From a distance, we might not notice anything at all. The mass of the black hole increases slightly. That's the only change. A huge planet might barely alter the black hole's size, making the event almost undetectable. There's no leftover debris, no heat trail, no visible sign. It's one of the few ways in the universe something can disappear completely. For scientists, this is frustrating. We rely on light, radiation, and motion to study cosmic events. But in a silent planet eating, there's nothing to detect. We might only notice a missing planet in a distant system. And even then, we wouldn't know where it went or when. This kind of destruction could happen to rogue planets, those that drift through space without a star. If one wandered near a black hole, there'd be no star to light up the scene. The planet would fall in and vanish. With no heat or gas, even sensitive telescopes would miss it. Some have wondered if this could happen to Earth. It's unlikely. We're far from any known black hole. But theoretically, if one passed close enough, Earth could be captured and dragged in. The process would be slow at first, but once close enough, we'd fall fast, and we'd leave no mark behind. There wouldn't be time for warning or escape. The gravitational pull would increase rapidly. Tides would rise, orbits would shift, and the sky would darken. Then the Earth would cross the event horizon and disappear. The sun might keep shining for a while, but one planet would simply be gone. Even for large black holes, planets are just snacks. Their destruction causes no fireworks unless the planet interacts with nearby gas. But if the environment is empty, the process is completely invisible. That's what makes it terrifying. No drama, just silence. It's possible that black holes have already consumed many planets in the universe. We just can't see it happen. When we observe certain black holes, we sometimes notice a sudden change in mass or orbit, a hint that they fed. But we rarely know exactly what they ate. As technology improves, we might catch more of these events. Future telescopes could detect small gravitational effects or shifts in infrared radiation. But for now, planet devouring remains mostly hidden, a process that leaves behind no light and no clues. Tidal forces tear things apart. Black holes don't need to touch an object to destroy it. Their gravity alone is enough. When something comes close, it's pulled more strongly on one side than the other. This difference stretches and compresses the object. These are tidal forces, and near a black hole, they become deadly. The closer you get, the more extreme the difference in gravity. A star approaching a black hole might be torn into a long stream of gas. A spaceship or asteroid would stretch and twist, pulled into spaghetti-like strands. This effect is known as spaghettification, and it's very real. Tidal forces happen because gravity weakens with distance. Your feet might feel more pull than your head near a black hole. For small black holes, this difference becomes lethal far from the event horizon. You'd be stretched into a thin line of matter long before you got close. For large black holes, spaghettification might happen much later, even after crossing the event horizon. But the result is the same. The object is pulled apart by gravity itself. No explosion, no impact, just pure gravitational tearing. It turns solid bodies into streams of particles. This process doesn't happen quietly. The torn-apart matter forms an accretion stream. It swirls, heats up, and glows with radiation. If the black hole is active, we might see a flash of X-rays or ultraviolet light. It's a cosmic flare, the final light from something being destroyed. Some stars don't fall in whole. They get shredded first. We call this a tidal disruption event. These are among the most energetic events in the universe. They can light up a galaxy for weeks or months. We've observed them from Earth using telescopes that detect high-energy radiation. One famous event, named ASSSN 14Li, showed a star being pulled apart and its material forming a glowing spiral. We could watch the black hole slowly consume it. It was like watching a cosmic whirlpool eat a sun. The tidal forces turned a massive object into glowing debris. Not all objects create visible flares. If the disrupted material is cold or slow, it might not emit much light, but the process still happens. The black hole doesn't care what the object is: star, planet, comet, spacecraft. If it comes too close, it gets stretched, shredded, and absorbed. The process is similar to what causes Earth's ocean tides, but taken to the extreme. On Earth, the moon pulls water more on one side than the other. Around a black hole, that difference in pull is enough to break atoms apart. It's the same physics, just more intense. These tidal effects also happen around neutron stars and other dense objects. But black holes take it further. Because nothing escapes their grip, even the torn pieces eventually fall in. The object isn't just broken, it's completely erased. Only radiation and gravitational waves remain. The stretching and spiraling leave behind patterns we can study. By analyzing the shape of the flare or stream, scientists can estimate the black hole's mass and spin. So even destruction becomes a tool. We learn about black holes by watching how they destroy things. Near a black hole, gravity doesn't just pull, it rips. Tidal forces turn solid objects into glowing ribbons of energy. That's the true power of curved space. You could see the back of your head. Near a black hole, light doesn't move in straight lines. The intense gravity bends space-time so much that light curves around the object. If you stood near one, without dying, you could see strange effects. One of the strangest? You could see the back of your own head. This happens because light can orbit a black hole. There's a region called the photon sphere, the distance where light travels in perfect circles. If you were just outside this zone, light from the back of your head could curve around the black hole and reach your eyes. It's a bizarre, mind-bending possibility. Of course, in practice, no human could survive that close. The radiation, tidal forces, and gravity would kill you long before. But theoretically, a camera or robot might record this effect. Simulations show how distorted the view becomes. Light from all directions gets bent, twisted, and smeared into rings. When scientists made the first image of a black hole in 2019, they saw this exact effect. The glowing ring isn't the black hole itself. It's light from behind it, bent all the way around. We're seeing light take a full loop, like a boomerang. The black hole warps the entire view. This kind of lensing is called gravitational lensing. Black holes are the ultimate lenses. They bend light from distant stars, galaxies, and even themselves. The closer the light is to the edge, the more it bends. That's why the image of a black hole shows a perfect glowing circle. If you looked at a black hole with a bright background behind it, you'd see rings and arcs. Some are called Einstein rings, perfect circles formed by light wrapping around. Others might look like smeared stars or twisted streaks. It's not just one image. It's many copies of the same light, bent along different paths. This effect doesn't only happen with black holes. Massive galaxies can also bend light, acting as giant lenses. But black holes do it on a much tighter, more extreme scale. Their lensing reveals how space itself is curved by gravity, not just objects moving, but light itself bending. Some simulations show that near a black hole, the sky would look like a swirling mess. Stars would appear in the wrong places. Some would be mirrored or flipped. You might see duplicates of the same star or the same object from multiple angles. It's disorienting, like looking into a funhouse mirror made of space. You'd also see time distortions. Light from objects closer to the black hole would be redshifted, stretched into longer wavelengths. They'd look dimmer and redder. Light from further away might look normal. The result is a strange, layered sky with warped brightness and color. This lensing effect isn't more than a visual trick. Scientists use it to study things we can't see directly. By measuring how light is bent, we can map dark matter, find distant galaxies, and confirm the presence of black holes. It's a powerful tool hidden inside a strange illusion. The idea that you could see the back of your head isn't just weird. It proves how different space becomes near extreme gravity. Light no longer travels the way we're used to. The rules change. So, near a black hole, even vision becomes distorted, not because of the eye, but because the very space between you and the light has changed. They hide in total darkness. Most black holes are invisible. That's not just a figure of speech, it's a fact. A black hole that isn't feeding emits almost no light. If it isn't surrounded by glowing gas or tearing apart stars, it doesn't shine. Some are so quiet that they emit less radiation than the cosmic microwave background, the faint leftover glow from the Big Bang. This means they are colder than the temperature of empty space. That's incredibly rare. Most objects in the universe glow in some way, even if faintly. But a quiet black hole, isolated and inactive, gives off essentially nothing. No visible light, no X-rays, not even a whisper of heat. Astronomers call these dormant black holes. They're not dead, they're just not currently eating. Like a predator that's full, they sit still and quiet. Without a nearby star or gas cloud to feed on, they remain hidden. Light doesn't bounce off of them, and they don't radiate. If such a black hole were floating nearby, we wouldn't see it with our eyes. Even telescopes would struggle. It could be massive, dangerous, and close, and still invisible. The only way to detect it would be by how it affects other things, stars, gas, or light that passes near it. Sometimes scientists spot strange motion in a star. It might wobble, flicker, or loop without any visible cause. These movements can reveal an unseen companion, often a black hole. The same goes for binary systems, where one star seems to orbit an invisible object. That's how many dormant black holes are found. In some cases, gravitational microlensing helps. When a black hole passes in front of a distant star, it bends the star's light. The star briefly looks brighter or distorted. That's our only clue, a flash caused by curved space. It's like watching someone walk in front of a projector screen and change the shape of the image. Even rogue black holes, ones floating alone through space, could be all around us. If they're not eating, they leave no trace. There could be hundreds in our galaxy alone, each one drifting quietly. Most we'll never see, but that doesn't mean they're harmless. Their gravity still works. If one passed close to our solar system, it could disrupt orbits, pull on planets, or fling comets our way. Even without light or heat, it would be deadly. And we might not detect it until it was already affecting the outer edges of the system. The fact that they can be colder than the cosmic microwave background makes them unique. That background is already only about 2.7 Kelvin, barely above absolute zero. A dormant black hole might emit less than that. It's not just dark, it's black in the truest sense. It doesn't glow, it absorbs. In theory, black holes emit Hawking radiation, but that's incredibly weak. For supermassive black holes, the radiation is so low it's undetectable, so they effectively give off nothing. They sit in the dark, growing only when something comes too close. Otherwise, they wait. This invisibility is what makes them dangerous. It's not their size or speed, it's the silence. Most things in space announce themselves. Stars shine, nebulas glow, but a dormant black hole could pass by unnoticed, and we'd never know. One merger could shake every planet. When two supermassive black holes collide, the entire universe notices, even if only slightly. The event sends out gravitational waves, ripples in the fabric of space-time. These waves stretch and squeeze space itself as they move. If the merger is big enough, those waves could reach Earth and affect everything here, including the orbits of planets. You wouldn't feel it. The shift would be smaller than the width of an atom, but it would be real. Your position in space would change slightly. Earth's orbit might wobble by a minuscule amount. The effect is tiny, but not zero. Every object in the solar system would move just a bit. This isn't science fiction. In 2023, astronomers reported evidence of low-frequency gravitational waves passing through the galaxy. These aren't the shark chirps from small black hole mergers. These are slow, rolling waves from massive mergers that happened billions of years ago, and we're just now detecting them. If two supermassive black holes merged in a nearby galaxy, the gravitational waves could shake our solar system. Not violently, but measurably. The wave would take millions of years to get here. When it passed, it would stretch and compress space-time as it moved. Everything, from atoms to planets, would shift slightly. It would be like the entire solar system briefly changed shape. No explosion, no sound, just motion through space itself. That's how gravitational waves work. They don't push things, they move the space between things. Current detectors like LIGO and Virgo catch quick, high-frequency waves. But new observatories like Nanograv and future missions like LISA focus on low-frequency ones. These are from massive events, galaxy-scale collisions, and billion solar mass black holes. These waves are much harder to detect, but they're everywhere. We think the universe is full of these giant waves. Every time galaxies merge, and that happens a lot, the black holes in their centers spiral inward. Eventually, they collide, releasing slow, powerful waves that ripple outward forever. Many of them are probably passing through us right now. Over very long times, these waves might influence star clusters or galactic structure. On short timescales, the effects are too small to matter, but still detectable. Timing arrays of pulsars, ultra-precise star clocks, are one way we're catching them. If a pulsar's signal arrives slightly early or late, that can indicate space was stretched. We haven't yet detected a single event shaking the planets, but the data is getting better. One day we might observe a merger, and calculate its direct effect on the solar system. That would be a major breakthrough, proof that cosmic events leave marks everywhere, not just where they happen. And what's truly wild is that the planets wouldn't know. The sun wouldn't flicker, there'd be no sound. But for a brief moment, all the distances in space would change. Then everything would return to normal, slightly shifted. That's the quiet power of gravitational waves. The next big merger might already be on its way. It could pass through Earth tomorrow, or 1,000 years from now. We won't feel it, but space itself will. And so will every planet, every moon, and every star. When black holes crash, the whole universe listens, even when it's silent. Magnetic storms on an epic scale. Near the event horizon of a black hole, magnetic fields become unstable and violent. The swirling matter in the accretion disk generates intense electrical currents. These create magnetic fields that twist, snap, and realign, often in milliseconds. The result? Magnetic storms more powerful than anything we've ever seen. These aren't like Earth's solar storms. They don't just disrupt communication or cause auroras. Near a black hole, magnetic reconnection can unleash more energy than billions of nuclear bombs. It happens suddenly, and it affects everything in the surrounding region. Radiation bursts, plasma jets, and particle flares all erupt at once. This happens because the magnetic field lines around the black hole get tangled. As matter spins inward, the fields twist tighter and tighter. Eventually, they snap and reconnect in new shapes. That release of energy is almost instant and incredibly powerful. Scientists call this magnetic reconnection. We see signs of these events in the form of X-ray flares. Black holes that are usually quiet suddenly brighten, then go dark again. These flashes can happen in seconds and fade just as fast. They often mark the end of a magnetic storm near the event horizon. The magnetic fields don't just cause flares, they help launch relativistic jets. These are beams of particles fired at nearly the speed of light. Without strong, structured magnetic fields, the jets wouldn't form. So the storms not only destroy, they also help shape how energy escapes the black hole's grip. These storms are chaotic. Magnetic turbulence makes the inner disk unstable. Matter heats up to millions of degrees. Electrons and protons crash into each other at high speed. The entire environment becomes a particle accelerator, far more powerful than anything we can build on Earth. This kind of activity might explain some of the brightest and fastest flares we've seen. When telescopes detect sudden X-ray or gamma-ray bursts from black holes, magnetic reconnection is a likely cause. The speed and intensity fit the model. It's like watching a storm unfold, just in radiation instead of wind and lightning. Some scientists believe these storms might help regulate black hole feeding. When the fields snap, they can eject matter that was about to fall in. This can create gaps or delays in how the black hole gains mass. So even though the black hole always wins in the end, magnetic chaos can slow it down. The patterns created by magnetic fields also affect the shape of the accretion disk. We see spirals, knots, and waves in light curves, signs that the disk isn't smooth. It's a stormy, volatile place where magnetic forces fight for control. And those forces help define how black holes evolve. We've started to simulate these storms using powerful computers. Models show field lines breaking and reconnecting in loops. They also help explain how black holes transfer energy to their surroundings. These simulations are essential since we can't send probes to see it directly. In the end, black holes aren't just passive pits. They're dynamic, violent environments. Their magnetic storms reshape nearby space, launch matter, and unleash deadly radiation. They don't just pull, they lash out. And when they do, the power is unmatched. storms of pure energy at the edge of time itself. Silent killers between galaxies. Not all black holes live in the centers of galaxies. Some wander in the dark spaces between them. These are called intermediate black holes, too big to be formed by a single star, but too small to be supermassive. They drift alone, far from stars or gas clouds, and unless they start feeding, they're almost impossible to detect. These black holes might form when multiple stars collapse together in dense clusters, or when several small black holes merge and then get flung into intergalactic space. Once they're out there, without fuel, they go dark. They emit no light, no signals, just gravity. They're called silent killers because of their invisibility and danger. A wandering intermediate black hole could cross paths with a rogue planet, a gas cloud, or even a star system. If it gets close enough, it will pull matter in. That feeding process can suddenly light it up, but until then, it's invisible. Astronomers suspect that thousands of these black holes are roaming the universe, not bound to any galaxy, not orbiting any star, just drifting in darkness. We rarely detect them, but some strange flares have been linked to them. A sudden X-ray burst in empty space could be a hungry drifter finally finding food. If one passed through our galaxy, it might not be noticed until it started affecting nearby stars. It could disturb orbits, trigger stellar collapses, or even start feeding. At that point, we'd see a sudden bright flare, a monster waking up. But by then, it could be too late to stop it. The scariest part? These black holes don't need to do anything to be deadly. Their gravity is enough. A silent, drifting black hole could pass near a solar system and alter its stability. It might send planets flying, shift asteroid belts, or disrupt orbits, all without glowing or leaving a trace. Some theories suggest that intermediate black holes could explain certain mysterious signals. Fast radio bursts, sudden high-energy events, or missing stars might all be clues, but proving it is hard. These black holes don't leave behind light, only effects. We've started to identify a few candidates. In some dwarf galaxies, strange movements hint at hidden mass. In one case, a sudden flare came from a galaxy with no active center, suggesting a wandering black hole found a meal. These rare events give us tiny windows into their lives. One day, future telescopes might track them more clearly. Gravitational wave detectors could catch their mergers. X-ray observatories might see more feeding flashes. But for now, they remain mostly unseen. Silent giants between the stars. Their existence tells us that the universe has no borders. Black holes don't need to stay inside galaxies. They can roam, wait, and strike without warning, and they could be anywhere, even close by. No roar, no glow, just quiet, drifting mass with the power to destroy entire worlds. Their shadow is larger than they are. When we look at a black hole, we're not seeing the black hole itself. We're seeing its shadow, a dark circle surrounded by glowing matter. But here's the twist. That shadow is bigger than the event horizon. What we see is actually a distorted image created by warped space-time. It's an illusion, and it's huge. The black hole's gravity bends light around it in extreme ways. Some light orbits it before flying off toward us. Other light comes from behind the black hole and curves all the way around. The result is a bright ring, the photon ring, and a dark center that appears much larger than the object itself. This shadow is about 2.6 times the size of the event horizon. That's because the light doesn't follow straight lines near a black hole. It curves, swirls, and wraps around. The more massive the black hole, the more dramatic the effect. What we see isn't a flat black disk, it's a warped projection of the hole's gravitational pull. In 2019, the Event Horizon Telescope captured the first image of a black hole. What we saw wasn't the black hole itself, but its shadow. The bright ring showed hot gas glowing as it orbited the hole. The dark center was the place from which no light could escape, the optical hole in space. This shadow proves just how much black holes bend reality. The light we're seeing has taken strange, looping paths to reach our eyes. It may have orbited the black hole several times. So when we see a photon ring, we're actually looking at light that's made multiple trips through distorted space. The shadow also shifts depending on the black hole's spin. A fast-spinning black hole creates an uneven ring, brighter on one side. That's because light moving with the spin gets boosted, while light moving against it is slowed. This asymmetry helps astronomers estimate rotation rates and mass. What makes this more incredible is that the shadow is visible even when the black hole itself is invisible. If there's a glowing disk or background, the hole still casts a shadow by bending light. It's like a silhouette carved into space by gravity. The shape reveals the true nature of curved space-time. In theory, you could never touch the black hole's surface because there is none. The shadow is just light being deflected. There's no object inside the outline, just a region where light can't escape. It's not a solid thing, but a boundary of influence, a trap for photons. Scientists use this shadow to test Einstein's theory of general relativity. The size and shape of the shadow match predictions exactly. That tells us space-time really is being warped the way we think. But it also leaves room for new ideas, like testing for hidden dimensions or exotic matter. Even though it's just an illusion, the shadow is more than a picture. It's a window into the most extreme environment in the universe. By analyzing it, we're studying gravity, time, and the nature of space itself. It's a map of invisible forces made visible. And what we see, that dark center surrounded by a fiery ring, isn't the black hole. It's the warped light left behind what we can never reach. A shadow, larger than the thing that casts it. Black holes might not just destroy, they could power entire civilizations. This isn't science fiction, it's based on real physics. A spinning black hole stores enormous energy, and in theory, it's possible to extract that rotational energy safely from the outside. The process is risky, but the reward is limitless energy. One proposed method is called the Penrose process. In this idea, a spacecraft drops an object into the ergosphere, the region outside the event horizon where space-time is dragged around. If done just right, the object splits and part of it falls in. The other part flies out with more energy than the original. The energy gain comes from the black hole's spin. You're stealing angular momentum from it. Over time, this could slow the black hole down, but it would take ages. Meanwhile, the energy output could be massive. Some estimates say up to 29% of a black hole's mass could be converted into usable energy. That's far more efficient than nuclear fusion or antimatter. It's the ultimate fuel source. If a civilization could safely orbit a spinning black hole, it could extract power using clever mechanisms, mirrors, particle beams, or magnetic fields. It would be dangerous, but incredibly effective. Another theoretical model is the Blandford-Znaick process. This uses magnetic fields and plasma to tap into a black hole's rotational energy. It's a more passive method, relying on electromagnetic forces. Some scientists think this is how real astrophysical jets are powered, nature's version of energy extraction. If an advanced civilization mastered this, they could build Dyson sphere-like structures around black holes instead of stars. These would collect radiation and beam energy to faraway locations. In fact, black holes might offer better long-term energy than stars because they last longer and don't burn out. The catch is safety. Get too close, and you fall in. Miscalculate the angle, and you're lost forever. You'd need incredible precision and control. But for a Type 2 or Type 3 civilization on the Kardashev scale, this might be possible. They'd use black holes the way we use hydroelectric dams, carefully but efficiently. We've already seen nature doing something similar. Some accretion disks glow with the brightness of entire galaxies. The matter falling in releases energy through friction, heat, and jets. If we could harness even a fraction of that output, we'd have more power than humanity could use in 1,000,000 years. This concept has inspired many science fiction ideas, from building cities around black holes to launching spacecraft using the energy extracted. But unlike most sci-fi, this is grounded in real physics. We just don't yet have the tools to make it practical. Even the simple idea of orbiting close to a black hole could offer advantages. Time dilation could be used for long-term storage, extreme computing, or observing deep time. It's not just energy, it's a whole new set of tools for advanced societies. So while black holes may seem like destroyers, they also represent untapped potential. With enough knowledge, they could be used, not feared. Some stars collapse without a sound. We usually imagine black holes forming in violent explosions. Massive stars reach the end of their life, blow apart in a supernova, and leave a black hole behind. But that's not the only path. Some stars might collapse into black holes silently, without any explosion. No flash, no bang, just gone. This can happen with certain stars that fail to produce enough energy to resist gravity. When they run out of fuel, they simply give up. Their cores collapse under their own weight. If the conditions are right, there's no outward blast, just inward collapse. The star disappears in seconds. These events are called failed supernovae. Astronomers think they might be common but hard to detect. The star shines one day and then vanishes. We don't see a dramatic death, we just notice it's no longer there, like a light bulb that turns off and never comes back on. White dwarfs, the remnants of small stars, can also collapse quietly under special circumstances. If they gain enough mass, say by stealing matter from a companion star, they can cross a threshold. That extra weight pushes them past stability. The result? A sudden collapse into a black hole, possibly without any visible warning. These events don't make shock waves. They don't throw out much debris. That makes them nearly invisible to traditional telescopes. But their gravitational pull changes. Nearby stars wobble, orbits shift. Over time, we realize something massive is there, something that wasn't before. Some star systems we observe today might be mid-transition, a white dwarf quietly gaining mass, a companion unaware of the doom it's feeding. Then, one day, the system changes and a black hole appears where a faint star used to be. No explosion, just a quiet transformation. This kind of collapse raises big questions about how common black holes are. If many are born without a supernova, then our current estimates might be too low. There could be millions of silent black holes we've never accounted for, lurking in ordinary-looking star systems. Detecting these events requires creative methods. Scientists monitor galaxies for missing stars. They also look for brief flashes of infrared light, signs that a star's outer layers fell inward. Future telescopes may catch more of these vanishing acts as they happen. It's eerie to think that something so massive can form without a sound. We're used to loud deaths, visible from across the cosmos. But in this case, Gravity does all the work. No light, no noise, just a quiet disappearance into darkness. If Earth's sun were heavy enough to end this way, we might not even notice at first. The light would keep reaching us for 8 minutes, then stop. We'd still orbit the black hole, unaware that everything had changed. A nearby one would mean apocalypse. Black holes don't need to touch Earth to be dangerous. If a black hole passed within a light year of our solar system, the effects could be catastrophic. Even without swallowing anything, its gravity would disturb the delicate balance of orbits. Comets, asteroids, and planets would shift. Chaos would follow. The first signs might be subtle. Outer solar system objects, like those in the Oort cloud, would start behaving strangely. Their orbits would tilt or stretch. Some would be ejected from the system entirely. Others would be nudged inward, falling toward the Sun and inner planets, including Earth. Over time, we'd see a rise in comet activity, more bright visitors in the sky, more close calls, more impacts. Earth would suddenly be in the crosshairs of a cosmic shooting gallery. Each comet would be a potential extinction event. And the source? An invisible gravitational menace far from view. The black hole wouldn't even have to enter the solar system. Just passing near the outer edge could be enough. The Oort cloud contains trillions of icy bodies, and they're loosely held. A slight tug from a nearby mass could send them on long looping journeys toward us. Some would take thousands of years, others would arrive sooner. If the black hole moved closer, the planets themselves would feel it. Orbits might stretch, tilt, or collapse. Earth's path could shift enough to change seasons, temperature, or climate. In extreme cases, we could be flung out of the habitable zone or out of the solar system entirely. We might not detect the black hole right away. It could be dark, cold, and small. Unless it was feeding on gas or stars, it wouldn't shine. We'd only see its effects: orbital changes, rising comet impacts, unusual gravitational shifts. By the time we realized what it was, it might already be too late. Some theories suggest this could have happened before. Periodic mass extinctions on Earth, like the one that wiped out the dinosaurs, might have been triggered by long-period comet impacts. A passing object, like a rogue black hole, could have been the culprit. There's no proof, but the idea is on the table. The worst-case scenario would be direct entry. If the black hole actually entered the solar system, chaos would erupt. Jupiter's orbit could shift. Saturn's moons could be stripped away. The inner planets might crash or spiral outward. Earth could collide with another world or be captured by the black hole itself. Even if Earth survived physically, the gravitational stress could alter our atmosphere, tides, and magnetic field. Weather could change permanently. Radiation from increased comet impacts could damage ecosystems. Civilization might fall long before the black hole reached us. In short, even a small black hole, just a few solar masses, could end the world from a distance. It doesn't need to touch us or shine. Its gravity alone is enough. That's what makes black holes so terrifying. They don't have to try. They just pass by, and the universe rearranges itself around them. Matter dances before death. Before falling into a black hole, matter performs one final dramatic act. It swirls, heats up, and shines brightly. This region is called the accretion disk, and it's one of the most energetic places in the universe. Gas and dust orbit the black hole at high speed, forming a glowing spiral. It's the last dance before destruction. As the matter spirals inward, it experiences friction. Particles crash into each other, heating up to millions of degrees. The disk emits light, not just visible light, but X-rays, ultraviolet, and more. Some disks shine brighter than entire galaxies. They're incredibly efficient at converting gravity into energy. What's strange is that the matter doesn't fall in immediately. It orbits for a long time, gradually losing energy. Like water circling a drain, it spirals tighter and tighter. The inner edge of the disk lies just outside the event horizon, the last stable orbit. Beyond that, there's no turning back. As the gas approaches the edge, time appears to slow from an outside perspective. We see the matter stretch, dim, and freeze near the horizon. In reality, it's falling, but the light takes longer and longer to escape. The disk flickers, shifts, and finally goes dark. That's the end. Some of the matter never falls in. Magnetic fields can fling it outward in powerful jets. These jets shoot out from the poles of the black hole at nearly the speed of light. So while some particles fall inward, others escape upward, like sparks from a fire swirling into space. These glowing disks help us detect black holes. We don't see the black hole itself, we see the light from the matter around it. The color, shape, and brightness of the disk tell us how massive the black hole is, how fast it spins, and what it's doing. It's like reading a fire by the color of its flames. Sometimes disks become unstable. Waves ripple across them, gaps form, sudden flares erupt. These signs tell scientists that the feeding process is chaotic. Matter doesn't just fall in, it fights, heats, and resists before surrendering. It's a violent, beautiful process. What makes it even more fascinating is that this dance might go on for years. A star torn apart by tidal forces might orbit the disk for a long time, stretching into glowing filaments. We've observed entire feeding events unfold over months, watching a black hole consume its meal piece by piece. And then it's over. The disk bims, the light fades. The last particles cross the horizon and vanish. All that remains is the black hole, slightly more massive, completely silent. The glowing spiral is gone, like footsteps erased by waves. But it leaves behind information. The radiation tells us what was eaten, how fast it moved, and how strong the black hole's pull was. Even in death, matter speaks, through light, heat, and timing. That's how we learn. It's a cosmic dance, full of motion, heat, and color. And the moment it ends is when we're reminded that nothing escapes forever. Not even light, not even beauty. A golf ball would weigh millions of tons. The density of a black hole is unlike anything else in the universe. Imagine taking something the size of a golf ball and giving it the mass of a mountain, or more accurately, millions of tons. That's what we're talking about when we describe black hole density. It's mass packed into almost no volume at all. This is especially true for small black holes. The smaller the black hole, the denser it becomes. If a black hole had a radius of just a few centimeters, it could still have the mass of the entire Earth. The numbers are hard to imagine. They break our usual sense of scale. Let's break it down. A typical golf ball weighs about 45 grams. Now picture one weighing several billion kilograms. That's what black hole density looks like. If you somehow placed it on Earth without destroying everything, it would fall straight through the planet like a bullet and keep going. This incredible density happens because black holes compress matter beyond the limits of atomic structure. At the center is the singularity, where all the mass is thought to exist in an infinitely small point. Space and time break down there. Physics as we know it stops working. No other object in the universe matches this. Even neutron stars, which are already insanely dense, aren't close. A teaspoon of neutron star material might weigh 1 billion tons, but a teaspoon of black hole matter? That concept doesn't even work. Inside the event horizon, matter stops having size in the usual sense. That's because black holes don't really have a surface. Their size is defined by the event horizon, the point beyond which nothing can escape. But inside that boundary, all the mass is thought to exist in a singularity, a point with zero volume and infinite density. It's not a place, it's an end. This leads to mind-bending implications. If you could compress Mount Everest into the size of an atom, you'd be on your way to creating a black hole. There's a limit to how tightly you can squeeze matter before gravity wins completely. That's what black holes are, gravity without resistance. And it's not just theoretical. Astronomers measure black hole mass using their gravitational effects. Some black holes are just a few kilometers wide, but weigh more than entire star systems. That's millions of suns packed into a volume smaller than a city. The gravitational pull from this density is overwhelming. Nothing can escape it, not light, not matter, not even information. That's why black holes are so terrifying. Their power doesn't come from movement or energy. It comes from their mass being packed so tightly together. We can't recreate this on Earth. Even our most powerful particle accelerators can't get close. We don't have the tools or energy to compress matter like this. Black holes form naturally from collapsing stars or extreme collisions, not by any process we can replicate. It's a reminder that nature operates on scales we can barely comprehend. A golf ball's size with the weight of a continent. That's what makes black holes more than just objects. They're physics pushed to its absolute limit. They are the heaviest emptiness we've ever discovered. Some shoot particles like cosmic blades. Not all black holes just sit there and absorb. Some of them launch. Near their poles, powerful relativistic jets fire particles at nearly the speed of light. These jets aren't visible beams like in sci-fi. They're more like cosmic blades, slicing through space with unimaginable force. They're narrow, fast, and devastating. These jets come from spinning black holes surrounded by accretion disks. As matter spirals in, magnetic fields twist into tight spirals. The energy gets funneled into two narrow streams, one shooting from each pole. These are the jets, and they can stretch for hundreds of thousands of light years. What's inside them? Charged particles, mostly electrons and protons, moving at relativistic speeds. That means near light speed. They're accelerated by magnetic fields and flung out like bullets from a cannon. We don't fully understand how the process works, but we see the effects clearly. These jets are so powerful that they can escape the black hole's gravity, not from inside the event horizon, but from the swirling energy outside it. They shoot through galaxies, pushing aside gas, dust, and even stars. Some create shock waves that shape entire regions of space. We detect them using radio, X-ray, and gamma-ray telescopes. From Earth, they appear as long, glowing streams. Some are straight, others are twisted or bent. They glow because the particles inside them interact with surrounding material, lighting up in extreme energy. One famous example is M87, the galaxy whose black hole was imaged in 2019. Its jet is enormous, extending over 5,000 light-years. It's so bright and straight that it can be seen in multiple wavelengths. It's a cosmic lighthouse, powered by a black hole billions of times heavier than the Sun. The jets can also affect how black holes feed. As they launch outward, they push away nearby gas. that limits how much matter can fall in, acting like a self-regulating system. The more the black hole feeds, the more it launches, and the more it pushes its meal away. Sometimes jets are angled toward us. When that happens, we call them blazers, and they're among the brightest objects in the sky. They pulse with high-energy radiation, flashing rapidly as they spin. These can interfere with signals, blind telescopes, or flood detectors with noise. It's strange to think of black holes, famous for pulling things in, also throwing things out. But that's exactly what these jets do. They're not coming from inside the black hole, but from the violent space just around it, a region ruled by magnetism, speed, and chaos. The energy involved is staggering. A single jet can carry more power than all the stars in a galaxy combined. It's focused, fast, and unstoppable, a cosmic beam that slices through light years of space like a blade. Black holes don't just consume. Sometimes they fire.
They never shrink, only grow. One of the strange rules about black holes is that their event horizon never gets smaller. According to the laws of physics, specifically the second law of black hole thermodynamics, a black hole's surface area can only stay the same or increase. It can't shrink, no matter what. This is similar to how entropy works. Entropy is a measure of disorder, and it always increases over time. Black hole surface area is treated the same way, as a kind of entropy. When black holes merge, the new black hole has a surface area larger than the sum of the originals. Even when a black hole emits tiny amounts of Hawking radiation, the process is so slow that the decrease is negligible. In normal circumstances, the black hole still grows. Every piece of matter or energy that falls in adds to its mass and expands the size of the event horizon. This means black holes are one-way doors. They take in energy, momentum, and mass, and never give it back. The event horizon, the point of no return, gets bigger with every bite, like a sinkhole that can't stop expanding, fed by the universe itself. We've seen this confirmed in gravitational wave data. When two black holes collide, the new one has a surface area larger than both parents. The math checks out. The universe follows this rule, one that seems almost designed to prevent reversals. This is part of why black holes are considered so stable. Once formed, they don't shrink, collapse, or unravel. They just wait and grow. Slowly, inevitably, they absorb more matter, more energy, and their event horizons stretch further outward. Even light adds to this growth. If a photon crosses the event horizon, it's gone, and the black hole gains just a tiny bit more mass. Enough photons over time make a difference. Every single interaction makes the black hole just a little bit bigger. This rule leads to some strange consequences. For example, if a black hole merged with a neutron star, the area rule still applies. No matter how extreme the interaction, the result must be a larger event horizon. It's like a rule the universe refuses to break. In theory, the only thing that could shrink a black hole is Hawking radiation, the slow leak of quantum energy. But for large black holes, this process takes longer than the age of the universe. So practically speaking, black holes only grow. This constant growth makes them cosmic archives. They keep everything they take in, mass, spin, charge, even if they never show it. They don't lose memory. They just build layers upon layers of space-time distortion. So when we say black holes are eternal, this is what we mean. They don't shrink. They don't fade. They only get bigger, darker, and more powerful with every second. They distort the map of the universe. Black holes don't just pull things in,
They bend the very shape of space around them. This warping of space-time is so extreme that it distorts how we see the cosmos. Through a process called gravitational lensing, black holes can make galaxies appear in the wrong place, duplicate them, or even hide them entirely. Gravitational lensing works like a magnifying glass in space. When light from a distant object passes near a massive black hole, it bends. This bending can stretch, flip, or duplicate the image. So one galaxy might appear as two, or a single quasar might look like a ring, thanks to the warped path of light. We've observed galaxies that appear to have halos, arcs, or mirrored images. These aren't special shapes, they're normal galaxies seen through a distorted lens. Black holes and other massive objects like galaxy clusters curve the space that light travels through. It's pure geometry, but it looks like illusion. Some of the most dramatic lensing comes from supermassive black holes. Their gravity bends light from behind them, revealing galaxies too far away to see otherwise. Sometimes, this lensing effect can make faint objects visible, letting us study the early universe. Other times, it hides objects completely. This means our map of the universe isn't straightforward. What we see is filtered through invisible curves. Some galaxies might appear closer or larger than they really are. Others may be missing entirely, their light scattered by cosmic obstacles. Space isn't a window, it's a funhouse mirror shaped by mass. In a few rare cases, lensing can create Einstein rings, perfect circles of light. These occur when a galaxy, black hole, and observer line up just right. The galaxy's light bends around the black hole, forming a glowing halo. It's a stunning sight and proof that gravity truly curves space. Lensing also helps us study dark matter. Since dark matter doesn't emit light, we track it by how it bends light from behind it. The same technique lets us see the mass of invisible black holes. A sudden brightening or distortion can signal a hidden object warping the light of something behind it. In fact, one way we find dormant black holes is by watching for unexplained lensing events. A star might suddenly brighten, then dim, not because it changed, but because something passed between it and us. That something might be a black hole we've never seen. Lensing affects more than just visuals. It changes timing too. Light from one part of a galaxy might arrive earlier than light from another, thanks to curved space. That creates echoes and delays we can study. It's like watching the same explosion from two different timelines. As we map the sky in greater detail, we keep finding these distortions. They're not flaws in the data, they're clues. They reveal hidden masses, new black holes, and the structure of the universe. Every bent ray of light tells a story. So when we look into space, we're not seeing it directly. We're seeing it through the bending lens of gravity shaped by black holes that may be billions of light years away. They twist the map without ever touching it. And that makes the universe harder to read, but far more fascinating. They suck the life out of stars. Some black holes don't live alone. They pair up with stars, forming deadly duos known as X-ray binaries. In these systems, the black hole slowly drains matter from its stellar companion. Over time, the star is stripped down, losing gas, heat, and eventually life itself. It's a slow cosmic feeding. This doesn't happen instantly. The star orbits the black hole at a distance, but not a safe one. The black hole's gravity pulls on the outer layers of the star, creating a stream of gas. That gas spirals into the black hole, forming an accretion disk, a hot, glowing sign of the star's decay. We detect these systems because they shine in X-rays. The matter heating up in the disk releases high-energy radiation. So, even if the black hole itself is invisible, the destruction it causes lights up space like a beacon. Some of the brightest X-ray sources in the sky are these violent partnerships. Over time, the star gets lighter and hotter as it loses mass. The black hole, in contrast, grows more massive and powerful. It's a one-way relationship. There's no balance. The star gives everything, and the black hole takes. Some systems last millions of years. Others end more quickly in collapse or explosion. In rare cases, the star may be torn apart completely. It could lose so much material that it can no longer support fusion. It dims, cools, and eventually dies, all while the black hole feeds. Other times, the star goes supernova, and the system becomes a double black hole, orbiting forever. We've observed many of these binaries in our galaxy. One famous example is Cygnus X1, the first widely accepted black hole candidate. It pulls matter from a blue giant companion, glowing brightly in X-rays. We've watched this system for decades, tracking the steady drain. Sometimes the feeding happens in bursts. The star might swell slightly, dumping a wave of gas into the black hole's disk. This creates a sudden flare of light, then a period of calm. These outbursts are unpredictable, making these systems both deadly and dramatic. The process depends on how close the star is. If it orbits too tightly, the black hole can devour it rapidly. If the orbit is wider, the feeding is slower and more stable. But in both cases, the outcome is the same. The star weakens, the black hole grows. These systems also emit gravitational waves if the orbits are tight enough. So in some cases, we can both see and hear the destruction. X-rays flash, gravity ripples, and somewhere in space, a star is being slowly erased. From a distance, it might look beautiful, a glowing swirl of light around a dark center. But up close, it's a violent process. The star is being consumed, cell by cell. There's no escape, no defense, no rescue. In these deadly duets, the black hole always leads the dance, and the star never stops giving until there's nothing left. Cauldrons of subatomic destruction. The space near a black hole's event horizon is one of the most extreme environments in the universe. It's a place where particles are constantly created and destroyed, where matter and energy collide in chaos. Scientists call this region a kind of quantum cauldron, boiling with invisible activity. It starts with the intense gravity. Near the event horizon, space-time curves so sharply that even virtual particles, which normally pop in and out of existence, behave differently. Some theories suggest that this region is constantly creating particle-antiparticle pairs, only to destroy them in flashes of annihilation. This is part of how Hawking radiation is thought to occur. If one of these particle pairs forms right at the edge of the event horizon, one particle might fall in while the other escapes. The escaping particle becomes real, stealing energy from the black hole. Over trillions of years, this could make black holes evaporate. But in the short term, this chaotic region is incredibly violent. Matter near the event horizon gets pulled, stretched, heated, and broken down to its smallest parts. Atoms are ripped apart. Nuclei are smashed. Particles collide with such energy that normal structure vanishes. It's not just gravity, it's temperature too. The accretion disk around a feeding black hole can reach millions of degrees. That heat tears apart molecules and ionizes atoms. Electrons and protons move freely, crashing into each other and forming short-lived particles under pressure. This region also accelerates particles to relativistic speeds, close to the speed of light. Collisions at this level can mimic the conditions just after the Big Bang. We learn about early universe physics by studying what happens near black holes. It's like having a natural particle accelerator in the sky. Magnetic fields make things worse, or more fascinating. These fields twist and snap, releasing bursts of energy. They accelerate particles, flip their spin, or send them spiraling into jets. Everything in this zone is moving, changing, reacting, all at incredible speeds. Some particles don't fall in right away. They might orbit the black hole for a while, bouncing around, hitting other particles, or even getting ejected. Others skim the horizon and vanish forever. Every microsecond, billions of particles are appearing, transforming, and being lost. We can't see these processes directly, but we detect their signatures. X-rays, gamma rays, and radio waves all hint at the chaos. They show us where collisions happen, where temperatures spike, and where energy gets released. Every flash tells a subatomic story. This region may also hold the key to understanding quantum gravity, the link between Einstein's theory of space-time and the rules of the quantum world. Right now, they don't agree, but the violent environment near black holes might offer the data we need to connect them. Near a black hole's edge, reality breaks apart into particles, energy, and heat. It's not just darkness, it's destruction at the smallest possible scale. The calm exterior hides the most extreme cauldron in the cosmos. They'll outlive everything else. Black holes are the longest-lasting objects in the universe. While stars burn out, galaxies collide, and even atoms decay, black holes just remain. They don't shine or move much, but their stability gives them near immortality. In fact, they'll be the final survivors of the cosmos, long after everything else fades. The only known way a black hole can disappear is through Hawking radiation. This process slowly leaks energy away from the black hole over time, but the rate is unbelievably small. For a black hole with the mass of our Sun, it would take around 10 to the 67th years to evaporate completely. To put that into perspective, the universe is only about 13.8 billion years old, or 1.38 times 10 to the 10th years. Hawking evaporation takes place over a timeline that makes galaxies seem like fireworks, bright, quick, and fleeting. Black holes live on for trillions upon trillions of times longer than the current age of everything. Even when stars are gone and galaxies have stretched apart, black holes will still exist. In the far future, when the universe enters what physicists call the dark era, the only objects left will be these massive remnants. No stars, no heat, just the slow evaporation of ancient black holes in total silence. The larger the black hole, the longer it lasts. Supermassive black holes, like the ones in galaxy centers, could take up to 10 to the 100th years or more to evaporate. That's a 1 followed by 100 zeros. Even the smallest quantum changes in space will happen long before these giants disappear. When they do evaporate, the process ends in a final burst of radiation. As the black hole shrinks, it radiates faster until it reaches a critical point and vanishes in a flash. But this isn't something we'll ever witness. It happens after everything else is already gone. By then, the universe will be unrecognizable. No more light, no more stars. Temperatures will be close to absolute zero. All particles will have decayed, except the ones locked inside black holes. They'll be the last holdouts of mass, motion, and time. This is one reason black holes fascinate physicists. They're not just extreme, They're eternal by cosmic standards. Even time itself seems to lose meaning near them. They represent the final pages of the universe's story long after any observers remain to read it. In a way, black holes are time machines pointing toward the end, not because they move through time, but because they endure while everything else changes. They persist beyond decay, beyond starlight, beyond matter. Their simplicity, mass, spin, and charge, hides their incredible permanence. Some theorists even suggest that black holes might outlast our universe completely. If space-time tears, resets, or births new realities, black holes could survive across transitions. It's a wild idea, but one grounded in their near indestructibility. Black holes won't just be the last thing standing. They'll be the last thing falling. They spit matter they can't consume. We often imagine black holes as cosmic vacuum cleaners, sucking in everything with no escape. But that's not the full story. Sometimes, when black holes try to feed, they fail. And when they do, they spit out matter in violent outbursts that can stretch across galaxies. This happens when matter falls toward a black hole but doesn't make it all the way in. Instead, the chaotic forces near the event horizon, heat, pressure, magnetic fields, become too intense. The result is a massive ejection of gas, dust, and radiation, thrown back into space. We've seen this process unfold in galaxies like NGC 5195, where clouds of gas are being hurled away from a black hole's core. These aren't slow drifts, they're explosive blasts, traveling at thousands of kilometers per second. It's like watching a feeding monster suddenly cough up its meal. Why does this happen? It turns out that not all matter that falls toward a black hole makes it past the event horizon. Some of it forms an accretion disk, heats up, and releases energy. The inner regions of the disk can become so energetic that they blow away incoming material. Think of it like a whirlpool spinning so fast that water flies outward instead of being sucked down. The forces near the black hole, especially magnetic turbulence and radiation pressure, can reverse the flow of matter. Instead of falling in, it gets launched out. These ejections are often seen as ultra-fast outflows, hot winds blasting out at nearly a tenth the speed of light. They sweep through galaxies, heating gas, halting star formation, and reshaping entire star systems. And this way, black holes don't just grow, they sculpt their surroundings. Astronomers believe these outflows help regulate galaxy growth. When a black hole feeds too aggressively, the outflows push back. They clear away gas that would otherwise form new stars. This feedback loop keeps galaxies from growing too large, too fast. It's a surprising twist. The thing that pulls the most also pushes the hardest. These outbursts are part of what makes supermassive black holes so important in galactic evolution. They're not passive eaters. They interact violently with their environment. Sometimes, the ejected material forms bubbles, massive, glowing structures filled with hot gas. The Milky Way has its own version, called the Fermi bubbles, enormous plumes rising above and below the galactic center. These are likely remnants of a past black hole feeding frenzy. What's incredible is that these events happen far from the event horizon. The material never actually touches the black hole. It's flung away from just outside, from the chaotic storm of energy circling the drain. The black hole doesn't eat it, it rejects it. So, while black holes do consume, they also explode. They don't just pull things in, they sometimes blast them out, rewriting the sky in the process. You'd never see someone fall in. If you watched someone fall into a black hole, you'd never see them cross the event horizon. From your point of view, they'd appear to freeze at the edge, slowing down more and more until they stopped moving entirely. It's not a trick, it's a consequence of how time and light behave near a black hole. This is because of gravitational time dilation. The closer someone gets to the event horizon, the slower their time appears to move relative to you. As they approach the edge, the light they emit gets more and more red-shifted, stretched to longer wavelengths until it fades away completely. So from the outside, it looks like the person is hovering at the event horizon forever. Their movements slow to a crawl, their color fades from normal to red to black. Eventually, their image disappears into the background, but they never appear to go in. Meanwhile, from their perspective, things are very different. To them, time feels normal. They fall past the event horizon in seconds and head toward the singularity at the center. There's no pause, no stop, just a rapid descent into darkness. Time only slows for observers watching from a distance. This strange disconnect between perspectives is one of the most bizarre parts of general relativity. It's not an illusion, it's a real difference in how time flows. Near a black hole, time and space trade roles, and the direction of movement becomes inescapably inward. The frozen image at the edge is a ghost, the last light that ever escapes from the falling person. As they move deeper, no more light makes it out, so what we're seeing is a recorded delay, not the real-time person. They're long gone, but their fading image lingers. Black holes don't just trap matter, they trap information. Every piece of light or data from someone falling in gets stretched out over time. Some theories even suggest that the person's entire history might be encoded on the surface of the black hole, part of the holographic principle. In practice, this means that black holes act like time machines in reverse. The past of whatever falls in becomes permanently encoded at the edge, but inaccessible to anyone outside. It's there, but unreachable. You can't retrieve it, only observe its final moments as time stretches to infinity. For physicists, this creates a huge paradox. If information never escapes, where does it go? Does the black hole destroy it, violating the laws of quantum mechanics? Or is it somehow preserved in subtle ways we don't understand? This is the information paradox, and it remains unsolved. But for everyday thinking, it's simply strange. You could watch a spaceship falling into a black hole and never see it vanish. Its final light would linger, slowed and dimmed, forever balanced at the edge of the abyss. And yet inside, it would already be gone. White holes might exist. Black holes suck everything in: light, matter, even time. But there's a strange idea in physics that imagines the opposite: white holes. These theoretical objects would be like black holes in reverse. Nothing can go in, and everything must come out. They're allowed by Einstein's equations, but we've never seen one. A white hole would be a region of space that expels energy and matter, possibly with incredible force. Unlike black holes, which have event horizons you can't escape, white holes would have boundaries you can't cross inward. Nothing, not even light, could enter a white hole from the outside. They could look like glowing cosmic fountains, radiation and particles pouring out, expanding rapidly with no apparent source. If white holes exist, they'd be short-lived or rare, because any small disturbance, like a dust grain or photon, might collapse them instantly into a black hole. Some scientists believe that white holes could be related to black holes. One idea is that every black hole could contain a white hole on the other side. Matter falls into the black hole, gets compressed, and eventually reemerges from the white hole, somewhere else, possibly in another universe. This ties into a version of the wormhole theory. A black hole might serve as one end of a cosmic tunnel with a white hole at the other. The journey between them would be impossible from our perspective, but particles or information might make the trip. It's theoretical, but fascinating. There's also a wild hypothesis that white holes might explain gamma-ray bursts. These are ultra-bright, short flashes of radiation from deep space. Some theorists wonder if they're failed white holes, brief moments where energy erupts but the hole collapses before stabilizing. Another twist, the Big Bang itself could be a kind of white hole. It expelled all the matter and energy in the universe from a single point, with no apparent input. Some physicists have explored the idea that our universe began as the out end of a black hole from somewhere else. White holes would break the arrow of time. They'd seem to run backward, undoing what black holes do. That's why they're hard to imagine and even harder to detect. We'd need to catch something spitting out mass, heat, and radiation without pulling anything in. So far, we've found no white holes. But the math that predicts black holes also allows white holes, so they're not nonsense. They're just elusive. They might be unstable or hidden in the early moments of the universe or simply too short-lived for us to find. If they exist, they could be keys to understanding quantum gravity or even time travel if connected by wormholes. They'd challenge what we know about cause, effect, and the direction of time. But until we see one, they remain a strange mirror to the darkness we do understand. White holes may never be found, but physics says they might be real.
Our universe might be inside one. It sounds impossible, but some physicists propose that our entire universe could be inside a black hole, not orbiting it, inside it. According to this bold theory, the Big Bang wasn't the beginning of everything, it was the result of a collapse from a parent universe on the outside. This idea comes from the way black holes behave. When something falls past the event horizon, it gets compressed to an unimaginable degree. But what happens next? Instead of crushing into nothing, maybe that collapse bounces, creating a new expanding bubble of space-time, like a newborn universe. This new universe would be sealed off from the outside, growing within the black hole. The event horizon becomes its boundary, and space inside continues to expand. From our point of view, it looks like everything began with a bang, but from the outside, if such a view exists, it's just another black hole. This leads to the black hole cosmology model, the idea that black holes don't destroy, they create. Each black hole might birth a new universe inside it. Our universe could be one of countless offspring in a larger, unseen multiverse, each with different physics, particles, and dimensions. It's not just fantasy. The equations that describe black holes and expanding space-time can be made to fit. The math works out in some versions of general relativity, and it helps answer tricky questions, like why the universe has the mass, temperature, and curvature that it does. If true, this would flip our understanding of the cosmos. We're not looking out into a black hole, we're living inside one. Everything we see, every star and galaxy, could be part of an internal reality born from a cosmic collapse in another world. It even fits with how black holes grow. From the outside, they appear stable, but inside, something dynamic might be unfolding, an entire universe with its own laws, time, and space. From our point of view, it feels endless, but we might be in a kind of bubble reality sealed by an event horizon.
This might also explain why we can't observe beyond the cosmic horizon, the limit of what we can see. It's not just distance, it might be a boundary, like the edge of a black hole's interior. What lies beyond it isn't more galaxies, it's the black hole's outer structure. It's impossible to test directly, but the theory opens up new ways of thinking. If black holes can create new universes, then maybe our universe is one of many, a branch on an endless tree, each leaf blooming from a collapsed core. It also adds a layer to the meaning of black holes. Instead of endings, they're beginnings. Instead of traps, they're gateways, not to other places, but to other realities. And perhaps every star that collapses is giving birth to something unimaginably vast. We may not be orbiting a black hole. We may be inside one.
Exotic matter can collapse into deeper voids. Most black holes form from collapsing stars, but there may be stranger kinds, born from even weirder material. Deep in space, exotic matter might create more extreme versions of black holes. These go beyond the usual models. They're rarer, more mysterious, and possibly more powerful. One example is the quark star, a hypothetical object made entirely of strange quarks. These stars would be even denser than neutron stars, hovering just above the black hole threshold. If one gained just a tiny bit of mass, it could collapse into an unusually compact black hole. Then there's the idea of boson stars, made from particles that don't follow normal matter rules. These objects could be incredibly dense and stable. If they collapse, the resulting black hole might behave differently than the ones we know, with unusual gravitational signatures. Some theories go even deeper, predicting the existence of Planck stars or other quantum objects that resist total collapse, only to burst or morph into black holes under extreme pressure. These would create black holes with different interiors, shaped by quantum effects we don't yet understand. Exotic matter might also affect how a black hole forms. If matter with negative energy exists, something predicted by some quantum theories, it could create voids that are more unstable, more chaotic. These wouldn't just bend space, they might twist or fracture it. These ideas tie into efforts to explain dark matter. Some scientists think dark matter might collapse under gravity to form black holes of a different kind, not made of atoms, but of unknown particles. These could roam the galaxy, completely invisible unless they interact through gravity. There's even speculation about mirror matter, a hypothetical version of matter that interacts through its own forces but not ours. If mirror stars exist, they might form mirror black holes, unreachable by light but just as heavy. Our instruments would only see the gravitational effects. In these scenarios, black holes don't just vary by size, they vary by type of matter. What collapses determines what's created. That means the universe could be full of black holes that look the same from the outside but have wildly different cores. We might not even recognize them. Some could be primordial black holes, formed from exotic matter in the early universe, not stars. They might be smaller, colder, and older than anything else. If they exist, they could account for much of the hidden mass in the cosmos. These deeper voids could behave differently, too. Their evaporation might be slower, their spin more erratic, or their gravitational fields shaped in strange ways. Some might create echoes in gravitational waves, or shine in unexpected patterns, subtle signs of their alien nature. We haven't confirmed any of these yet, but the more we learn,
the clearer it becomes. Not all black holes are created equal. Some might be deeper, weirder, and more dangerous than anything we've encountered. Black holes are strange enough already. But some may come from matter stranger than fiction. They built the first galaxies. We often imagine black holes as destroyers, but in the early universe, they may have been builders. Right after the Big Bang, the cosmos was filled with hot gas and darkness. And in that chaos, the first black holes may have formed, long before the first stars. Tiny, dense, and hungry. These early black holes likely came from massive clouds of collapsing gas, not stars. Some may have been primordial, created in the high-energy moments just after the Big Bang. Others may have formed from huge collapsing structures, directly skipping the star phase entirely. Once formed, they started pulling in nearby matter. As they fed, they created gravitational wells, deep pits in space-time. These pits helped gather more gas, forming clumps that would later become galaxies. Instead of tearing things apart, they pulled the building blocks together. This is one of the great paradoxes of black holes. The most destructive objects we know may have been essential to galactic creation. Without them, stars might never have clustered into galaxies. The early universe might have stayed scattered and formless. Observations show that most large galaxies have a black hole at their center, even ones formed just a few 100 million years after the Big Bang. That means black holes were already there, shaping their environments. Their gravity organized chaos into structure. As galaxies formed, the central black holes grew. They pulled in stars, gas, and dust, forming bright quasars that lit up the early universe. These quasars outshone entire galaxies and helped reheat the cosmos, turning cold, dark gas into glowing matter again. Simulations of galaxy formation show that you need black holes to make things work. Without their gravitational pull, galaxies would collapse too slowly or unevenly. With them, you get spirals, clusters, and structure. Black holes aren't just passengers, they're architects. Even today, the size of a galaxy is linked to the size of its central black hole. It's called the M-sigma relation, a mysterious rule that connects the invisible monster at the center to the behavior of all the stars around it. Nobody fully understands why the link exists. But it suggests something deep. Galaxies and their black holes grew together, influencing one another. Black holes fed from the galaxy's material and in return shaped its development. Their outbursts, jets, and winds pushed gas away, slowed star formation, and maintained balance. The idea that galaxies needed black holes flips our intuition. We often think of gravity as a trap, a collapse into nothing. But in the early universe, black hole gravity gave shape to the formless void. It concentrated the raw material of stars and planets. Without black holes, there may have been no galaxies. And without galaxies, no stars like our sun, no planets, no life, no us. In the beginning, it wasn't just light that formed the cosmos. It was darkness. Aliens could compute faster near one. Time slows down near black holes. This isn't science fiction. It's a proven result of Einstein's theory of relativity. The stronger the gravity, the slower time moves. And near a black hole's event horizon, time nearly stops. For advanced civilizations, that could offer a strange opportunity to think faster. Imagine a super-intelligent species building a colony just outside the event horizon. From their perspective, outside time races ahead. A second for them might be hours or days for the rest of the universe. That means they could run simulations, process data, and evolve ideas at an accelerated rate. This is called gravitational time dilation. It's not just theory, we've measured it near Earth, and it becomes extreme near black holes. Some scientists have wondered if this effect could be used as a kind of thinking accelerator for advanced life forms or artificial intelligence. A being near a black hole could observe billions of years of cosmic history in what feels like a few minutes. Galaxies would evolve and die. Civilizations would rise and vanish, all while they experience only brief moments. It would be like watching the future unfold in real time. The trade-off? The environment is deadly. Temperatures, radiation, tidal forces, all of them become more intense the closer you get. A physical body might not survive, but machines, or purely digital minds, maybe they could handle the pressure. Maybe they'd embrace the risk to gain the time advantage. There's even a theory that AI civilizations might seek out black holes for this reason, not to escape, but to accelerate learning. They could hide just above the event horizon, storing massive data archives, processing ideas faster than anywhere else in the universe. Some speculate that advanced species may have left the galaxy's outskirts and migrated inward toward the supermassive black holes at the centers. We wouldn't see them. Their signals would be delayed or redshifted beyond recognition. They'd be thinking too fast for us to notice. Of course, this is all hypothetical, but it makes you wonder, are we looking in the wrong places? Instead of searching for signals in open space, maybe we should be watching the edges of black holes for unusual heat, energy spikes, or strangely stable structures just outside the void. This concept also raises questions about subjective experience. What would it feel like to live near a black hole? Would time feel normal to you while stars explode and galaxies fade and fast forward outside your window? Would you feel like a god or a prisoner? The deeper you go, the slower time moves. In theory, you could approach a black hole and witness the entire future of the universe play out before you cross the horizon. It's not a journey anyone could survive, but it's a concept that keeps scientists awake at night. Black holes don't just bend light, they bend time. And maybe, for the right minds, that's a feature, not a flaw.
They'll be the last survivors of time. When everything else has faded, black holes will still remain. Stars will burn out, galaxies will dissolve, even atoms will eventually decay. But black holes? They'll sit in silence, holding the last pieces of matter in the universe, cold, dark, and unstoppable. We call this the heat death of the universe, the point where all usable energy is gone. No more light, no more movement, just an endless expanse of low-energy particles. The only exceptions will be black holes, scattered across the dark like silent tombstones of a brighter past. Even then, they'll continue to absorb whatever's left: particles, radiation, random waves of energy. Every bit of matter that drifts through space will eventually fall into one, and the black hole will grow, becoming the final sink of everything that ever was. This process could take trillions upon trillions of years, but time means little to a black hole. It doesn't rot, it doesn't fade. It simply waits, pulling everything inward. It is the most patient object in the universe, powered by gravity and ruled by silence. Eventually, even black holes will begin to evaporate through Hawking radiation. But this process is unimaginably slow. A supermassive black hole may take up to 10 to the 100 years to completely vanish. That's a number so large it defies understanding, longer than the age of stars, atoms, or memory.
In their final stages, black holes shrink faster, releasing heat and light in one last quiet flash. Then they're gone. But by then, the universe will be utterly dark. Nothing will remain to see their final breath. The last black hole will die alone. Until that moment, black holes will remain the universe's final structures. No stars, no galaxies, no planets. Just these dark scars left behind by everything that came before. They'll be the closing punctuation of existence, a final echo before eternal silence. This end state isn't science fiction. It's one of the leading models in cosmology. All signs suggest the universe is expanding forever, cooling and thinning out. That means black holes won't be erased by some new event. They'll simply outlast. In this way, they become the keepers of cosmic history. Everything that has ever fallen in, from stars to information, stays trapped inside. A frozen library of the universe's past, sealed shut by gravity, unopenable by any means we know. They won't move, they won't shine, they won't decay until the very end. But they'll endure as long as endurance is possible. They'll be the last observers, even if they observe nothing.